everyone. Good morning. Mihaji Redman is an honor student, and he finished his research in this topic. The title of his presentation is Matrix Mesh Communication Protocol. This one is about something like an instant messenger, like WhatsApp or something similar. But it's used for special purposes. So that's the basic idea. And I think now it's time for Mihaji to present.
Thank you. Thank you. Can I start? Good morning, everyone. My name is Minhajur Rahman, and I'm a computer science student. Today, I'm here to present my undergraduate thesis defense. My thesis is about the matrix mesh communication protocol, and I work with Dr. Yinghui Wang for this thesis. Before I start, I would like to outline my today's talk. First, I will give a quick overview of matrix mesh and the motivation of this research. Next, I will go through relevant background information in detail, including relevant architectural models, cloud computing, as well as relevant technologies and algorithms, including matrix mesh. Following that, I will get into the design and implementation of matrix mesh and relevant technological considerations. Finally, after looking at the results, I will discuss future development and make some closing remarks. Matrix mesh is an instant messaging protocol that is based on cloud architectural model and computing principles. It is intended to facilitate communication during disastrous conditions, which is here refers to any situation that breaks communication with the server, such as problem with the server or problems with internet connection, as one might encounter during a natural disaster or similar problematic event. The protocol is not built entirely from scratch, but extend the existing matrix protocol. Keeping these disastrous conditions in mind, matrix mesh categorized possible network connection states into the following 4 levels. In level 1, there is a full functioning internet connection. Level 2, the application server is not available, but the internet is still available. In level 3, the internet is not available, but the local area network is available. In level 4, the internet and local area network connections are not available, but battery operated mobile devices are still available to provide personal area network or near field communication connections. The proposed messaging protocol is designed in such a way as to follow application to extend the protocol easily, so as to provide some level of communication support at all the 4 considered network connections levels. Communication plays a very important role in our day-to-day life, allowing people to connect with each other and share information. In the modern era, we are given ourselves many different tools to help us make these connections, from instant messaging to video calls. The internet has been crucial to the development of this new era of connections, and as such, it is not surprising that most modern communication technologies rely on internet connections. This means that without internet connectivity, communication systems that are currently relied on become unavailable. Worse still, many of these technologies rely on centralized cloud-based services, which can be brought down by a few lines of accidental code. Thus, in times of disaster or turmoil, it is unreasonable to expect these services to operate continuously, in some case, to operate at all. Additionally, as infrastructure is not equally well distributed across the globe, there are many places where an internet connection is far from guaranteed, even under normal conditions. Further, as climate change continues to increase both the frequency and severity of extreme weather events, disruption will only become more likely. As such, matrix mesh was proposed to provide alternative means for vital communication. The client-server architecture is very commonly used architecture based on distributed computing principles. In this model, the tasks are split between software on the server computer and the client computer, such that clients on remote host request services from the central server. Server wait for requests from the client side and respond based on those requests. A standard client-server architecture implementation may provide resources and services such as account, group management, message relaying, client isolation, and so on. Applications successfully implementing this architecture can be very efficient while allowing the client to be relatively simple. A major problem with this architecture, however, is that it has a single point of failure: the server. If the server is ever unavailable, the system becomes unavailable to function. Peer-to-peer architecture is another commonly used computer network architecture. In this model, each node serves as both client and server simultaneously. In many ways, the opposite of the client server, and peer-to-peer does not rely on any specific server, and thus does not have any single points of failure. As a result of being completely decentralized, peer-to-peer is very resilient to changes in peers. For example, if one peer leaves, there is a minimal impact on the overall networks, as other nodes will provide the same functionalities. Due to the pure distributed architecture, if there is a large group of peers in the network at the same time, the network can handle the correspondingly large load easily, as that load is distributed among a proportionally large number of nodes. This scalability is the reason that it's used in some instant messaging applications, file sharing system, high performance computing application, among others. However, in the peer-to-peer model, each client is likely to have to take on heavier duties in terms of maintaining communication across multiple connections with a variety of peers. The scalability does not prevent service slowdowns due to heavy loads. They are mitigated as all peers not only consume but also contribute resources. Cloud-Dew architecture is basically an extension of the client-server model. In the Cloud-Dew model, participants are classified as either cloud or Dew server, where the Dew server operates on a local device and acts as like a web server. The core functionality of a Dew server includes providing the client with services similar to what the cloud server provides and synchronizing its database with the cloud server database. A cloud server refers to a regular server residing in the cloud, which operates similarly to a standard server. A Dew server is lightweight and usually serves only one user, the client, storing only data pertaining to that user and their needs. The Dew server and its data may disappear easily for different reasons, such as hardware damage. However, the vanished Dew server can be recreated if necessary, as all the requisite data exists in the cloud server. One particular interesting and useful feature of Dew server is that they are accessible with or without an active internet connection, as it is running locally. Dew computing and the associated Cloud-Dew architecture arise naturally when the cloud-based activities and services interact with local devices. By definition, Dew computing is an on-premises computer software paradigm where the on-premises computer provides functionality which is independent of but also collaboration with cloud services. On-premises computer in this conceptualization might be local computers, potentially including personal computers such as laptops, desktop, tablets, mobile phones, and other smart devices. Independence refers to the ability of the on-premises computer to be able to provide functionality while offline, where collaboration refers to how the Dew computing application exchange information which cloud service during its operation to facilitate its independence operation. Such collaboration may include synchronization, correlation, or other types of interoperation. The goal of Dew computing is to realize the combined potential of both on-premises and cloud-based services. A key feature of Dew computing would be microservices operating in collaboration with macroservices, which is to say Dew service in collaboration with cloud services. As a codified concept, Dew computing is relatively new, while Dew computing applications are not. As Dropbox, Google Drive Offline, OneDrive, among other cloud interfacing applications satisfying Dew computing requirements, have implemented analogous to Cloud Dew architecture. Dew computing is not separate from cloud computing, but instead it is a post-cloud computing era paradigm which tries to determine to organize non-cloud components in the cloud environments. Communication technologies are tools and equipments which facilitate the sending, receiving, and processing information. The development and modern ubiquity of the internet has revolutionized the flow of information, both complementing the other technologies that contribute to be used. While facilitating the development of entire new tools such as the establishment of messaging system, instant messaging is a text-based communication in which typically two people participate in a conversation, typically via a personal device. Instant messaging can be differentiated from chat, where the user participates in a more public, real-time conversation within a chat room. Software establishes functionally direct connection between users, ideally passing the message synchronously. Given this goal, technological considerations are becoming important. Auxiliary data links include Wi-Fi, Bluetooth, near-field communication, NFC, and other similar technologies. Often, these links are used for communication at specific range. Bluetooth is one of the more widely supported of this technology and has no dependence on Wi-Fi or internet connectivity, making it a good candidate for an alternate connection technology. Wi-Fi is now common wireless technology which can be used to connect a personal computer, mobile phones, and other devices to the internet. The term Wi-Fi does not stand for anything, but is often thought to be from wireless fidelity. It is based on the IEEE 802.11 family of standards that is most commonly used for local area networking of device and internet access, allowing nearby digital devices to exchange data via radio waves. Wi-Fi compatible devices are able to connect to the internet via wireless local area network and wireless access point. Each wireless local area network has an access point which is responsible for receiving, transmitting data both to and from users. The two varieties of connections are ad hoc mode and infrastructure mode. In infrastructure mode, usually needs at least one access point, with which clients such as laptops, smartphones associated themselves, allowing them to send their data to the terminal, which thereafter transmits the data into the correct destination. Infrastructure mode can be further divided into two different submodes: basic service set (BSS) and extended service set (ESS). In BSS, there is only one access point, whereas in ESS, there are two access terminals. Sorry. I apologize for that. weird. Yeah.
I don't know what I can do, it's his computer. There's not much I can do to it. I don't even know
Yeah.
where it came from. Well, I think the problem is when he tries to open up his machine right now, like it's
Should
coming
I,
up on a display that's
like,
not.
I'm gonna restart it.
Okay. It possibly could be, but if he brings it up on the internal system, it's no longer on the stream. He'll be lost at that point, but it's up to him.
It's more important that we present now.
Yeah.
Than be on the screen.
I'm restarting quickly.
Okay. You want to set your configuration to mirror your screen, not
Yeah.
split. Yep.
Huh.
Yeah.
Somehow.
We're not seeing your icons on here, so you're on
Settings. Display. Built-in display. I'm not mirroring. Yeah. That's
I don't know
everything
why
could.
you don't have a setting there to tell it not to span.
I. Thank you.
Okay, I'll let you guys.
What's the USB-C port? Thank you.
No, it's the wrong type. We'll need yours, Yingwei. Yeah, that's for a phone. Just plug that into the side.
So I want.
Yeah, we see your screen now. Just get the camera reset to you.
I changed 2 slides afterwards.
Oh, great. That's not really good for us, but oh well. We probably have to. I can shut down and restart the resync utility.
If
Just
the
a
screen
second.
doesn't work, that's not working, so.
Okay. Your call, ma'am.
Well, it just,
Yeah.
just wanna move on.
Monsieur, on phone. No, I'm just getting my phone to approve the access.
That verification. I hate that thing. And it doesn't work particularly well unless you switch applications, and like then it will not do it. You have to get the code number and punch the code number. It's the only way to do it. Yeah. Yep.
I forgot where I left off. Okay. Wi-Fi is now a common wireless technology which can be used to connect personal computers, mobile phones, and other devices to the internet. The term Wi-Fi does not stand for anything but is often thought to be from wireless fidelity. It is based on the IEEE 802.11 family of standards that is most commonly used for local area networking of devices and internet access, allowing nearby digital devices to exchange data via radio waves. Via this exchange, Wi-Fi compatible devices are able to connect to the internet via wireless local area network and wireless access point. Each wireless local area network has an access point which is responsible for receiving, transmitting data both to and from users. The two varieties of connections are ad hoc mode and infrastructure mode. Infrastructure mode needs at least one access point with which clients such as laptops and smartphones associate themselves, allowing them to send their data to the terminal, which thereafter transmit the data to the correct destination. Infrastructure mode can be further divided into two different submodes: basic service NAT (BSS) and extended service NAT (ESS). In BSS, there is only one access point, whereas in ESS, there are two access terminals such that user may roam by passing from one terminal to another without interrupting their connections. Ad hoc mode notably operates without the intervention of an access terminal, so clients are able to communicate with each other directly, which is also referred to as point-to-point communication. If infrastructure mode is unavailable, this can function as an auxiliary link. Bluetooth falls into wireless personal area network category and use radio frequency in the 2.4 GHz band along with several types of Wi-Fi. It is short range and point-to-point and ad hoc, making it ideal for theoretic situation. And again, it is widely adopted and available when Wi-Fi and internet connectivity are not, while also being adequate secure. Bluetooth architectures allows for two types of network: piconets and scatter nets. A piconet constitutes one primary or master nodes and 7 active secondary nodes called slave nodes, giving a total of 8 active nodes which are all present within the requisite of 10 meters. The communication between the primary and its associate secondary nodes may be either one-to-R or one-to-many, where communication occurs only between masters and slave nodes, and slave-to-slave nodes communication is not possible. In addition, there are maybe up to 255 part nodes which are also secondary nodes but cannot take part in communication unless activated. It is also possible for piconets to overlap with the slave in one NAT, acting as a master in another, becoming a bridge node. These bridge nodes, which cannot be stations, may receive a message from its master in one piconet where it is a slave, and then deliver that message to a slave node in the piconet for which it is the master. This interconnected structure of piconets is termed a scatter NAT. A push notification system is a messaging system used with mobile phones. Typically shows up pop-up message to user device. It generally consists of a title, a message, an image, and a URL. Push notifications are important as they can deliver real-time updates and reminder. Generally, there are 4 types of push notification: web, desktop, mobile app, and wearable. For this research purpose, we will focus on mobile app push notifications, specifically Android. Mobile app push notifications are triggered by downloaded application on the user device. Whenever a user opens the downloaded app, unique identifiers are registered for both the app and the device with the operating system's push notification service. These IDs are then shared with the app publisher, allowing for push notification to be sent correctly. The Android operating system opts the user into this notification by default, allowing manual user opts-outs, where iOS requires the user to first agree to receiving messages before push notification may be sent. To send push notifications to user, apps need to be properly configured and registered with push notification services. In the Android push notification system, it is typical for the app to have associated Firebase project and authentication keys, allowing for push notification to be sent via Firebase Cloud Messaging, FCM. App notification to users are sent through FCM to Google, with its server replying the notification as appropriate to the designated device or devices. Firebase Cloud Messaging, or FCM, is a cross-platform messaging system used to send notification in Android, iOS, and web apps. Notification messages may be sent to single devices, to a group of devices, or to all devices subscribed to a specific topic, while also allowing for return messages to be sent via the FCM connection channel. The key components involved in the transfers are a service that instance target messages and target a service that builds and target messages, either a trusted server supporting appropriate protocols or other notification composer that forms a part of FCM. The FCM backend handle message request and then performs appropriate secondary services such as message duplication by topic and message metadata generation. The platform level transport layer performs any required platform specific configuration and delivers the message to the target device. The 3 platform layers are the Android transport layer, the Apple push notification service, and the web push protocol for web apps. The FCM SDK on the user device, which displays the content appropriately based on the associated app's state logic. The Matrix Instant Messaging Protocol is both open and decentralized. In many ways, it is function similar to the Single Mail Transfer Protocol, or SMTP protocol, for email. As in SMTP, communication occurs between independent service provider, which in case of Matrix are its home servers. It is sometimes considered to be a decentralized conversation repository, drawing attention to its similarities with Git repository management. In that messages are duplicated across all participants and their home servers, so as to maintain a robust and decentralized record of the conversations. Thus, in Matrix, there is no single point of failure, and if a server is ever unavailable to the conversation, can continue until its return. In Matrix, there are many home servers. Each of them can be considered as a messaging service provider. A user must create an account on a home server, and each home server must connect to others so that messages can be passed between them. To communicate, a user must join a room, and the room data is duplicated across all home servers whose users are participant in the room. As a result, no single home server has control of the room. Here we see a depiction of the Matrix protocol. We can see that it has a layered architecture and that the internal components are well defined, generally with minimal coupling with other components. This design helps to ensure that future alteration and additions, such as addition with regards to encryption, are easily implemented and have impacts with limited and well-defined scopes, facilitating improvements and backwards compatibility. The matrix mesh protocol will make use of all features of the matrix protocol, and in standard condition will function more or less identically. In situation where that functionality would not be possible for matrix, it will take advantage of a hybrid architecture, transitioning to a more peer-to-peer structure supported by the CloudDew architectural model. As such, it is possible to think of the client as having two components, a UI element with which the user interacts, and a Dew server which manages data and transmission related services. As per the CloudDew model, this Dew server will be able to function as both a client and a server as appropriate. The UI only operates when required by the user. However, the Dew server will function continuously to maintain consistency. The Dew server deals primarily with data management and transmission, not with user interaction of data display, which should be dealt with by the UI portion of the client. Under normal conditions, a Dew server does not need to keep connection with other clients. However, in situation where network functionality is an issue, a Dew server should maintain such connection to support its own function to provide service to other clients. This is vitally important as the users of these other clients should provide help to others in the event of disaster. While in client server mode, the server will maintain account information and establish connections among clients. In peer-to-peer mode, emergency condition will be assumed so that the system does not need to provide complete administrative and advanced services, which will help to keep the client lightweight. Importantly, the UI does not communicate with external servers or clients, but only with the Dew server. From the viewpoint of the user using the UI, as long as the message is sent to the Dew server, it is already sent, with any remaining work being the responsibility of the Dew server. The design goal of the extension is to provide an additional connection using Bluetooth to allow an alternate means of connection in situation when an internet connection with a home server is not possible, at which point this Bluetooth link will allow peer-to-peer communication to continue a bit at short distance. However, communication between users that are in close physical proximity will still be possible, as message replication across user will allow messages to eventually reach other devices. In Matrix, user will be remembered to the same room if they are chatting, with the encryption tied to the room. Further, as message for a room are replicated across all participants, allowing messages from one participant to propagate others. As such, the design consideration include incorporating Matrix and its feature as much as possible, with as few alterations as possible. The primary goal is to extend Matrix functionality through the use of auxiliary data links, allowing standard Matrix functionality to be the norm, while transitioning to a parallel auxiliary data connection when that is not possible. Bluetooth is used for that auxiliary data link for the reason detailed earlier, in order to produce a proof of concept. To minimize the development time, we decide to use existing Matrix client. There are lots of open source Matrix client already, such as DittoChat, NeoChat, FlappyChat, and Element. We determined that it would be best to use something cross-platform for expediency and reusability in future. So we had two options: DittoChat, which was built in React Native, and FlappyChat, which was built in Flutter. React Native and Flutter are both widely used for cross-platform application. However, during our exploration of the options, we noticed that DittoChat did not seem to have much recent support, while FlappyChat has had continuous updates. In addition, Flutter has advantages over React Native in that Flutter also supports desktop application using the same code base, while React Native does not. So based on those considerations, we chose FlappyChat over Ditto, with the goal of transitioning it from Matrix to Matrix Mesh. Bluetooth support was sourced from existing Flutter package, and through this we added this functionality to the Matrix link layer and messenger client settings so that it can be turned on and devices may be searched for in order to connect to them easily within the app. Once there is a Bluetooth connection, messages can be passed using the same UI and controls as in normal functionality. Messages sent to user via this connection will eventually propagate to others, and once connectivity is restored, will integrate into the standard Matrix server. Taking advantage of Matrix eventually consistent data model. The proof of concept Matrix Mesh client implementation is open source and available on GitHub. In the pictures, first we see the Bluetooth devices and settings menu that was added to the Flappy chart. Settings user interface to allow for management of device connections. On this page, available devices that are in range can be chosen and connected to. Once devices are paired and connected, the user need only return to standard chat interface to send messages. Matrix already supports encryption, which you can enable, allowing messages to be encrypted should passing the messages in this way be a concern. As this is just a proof of concept, there is a lot of room for future development. For instance, we might try to add other auxiliary data links to the link layer, and we could improve all the existing existing encryption via the TOX protocol. Additionally, a better user interface could be developed. In addition, this could be transitioned to a full Matrix client instead of just a proof of concept. Finally, Matrix Mesh improves vital communication in difficult conditions, potentially providing crucial connectivity in difficult situations. The use of Matrix means that users may send message across Matrix service providers over multiple links and via bridging applications onto other networks. Additional research and extension of this proof of concept is possible, and there is a room for additional development. Thanks so much for listening. I would like to thank my supervisor, Dr. Wang, and my honors committee and the School of Mathematical and Computational Sciences for giving me the opportunity to perform this research. And there are some resources that used for this research. And thank you. I'm ready to take questions.
Once again, for those just arriving, if you have questions, come on up front, come between here, and stand in front of the camera so that the people watching the stream or watching the recording later can hear you.
So, the committee an opportunity.
Hi.
So, can you show us what was done before and what is your contribution to this project? This is very important because I noticed that it's not the general observation. So students when present something, they present something like everything is theirs or nothing is theirs. So you have to know exactly what is yours and what is not yours.
So this portion here. So this basically, this is the Flappy chart that's open source that already use Matrix. And as we said, we're gonna extending Matrix Mesh, Matrix and transition into Matrix Mesh. So in the Matrix architecture, here, this is the Matrix architecture. In the link layer, we add additional auxiliary data link in the link layer. So basically, on the HTTP connection already handled by the Matrix, and we add auxiliary data links Bluetooth on that as a proof of concept. So later on, local area network and other auxiliary data links that I mentioned can be added there. So that was the part here it's showing. So there is in the devices you have in the link layer I added Bluetooth connection. You selected Bluetooth from there, and then once the Bluetooth gets connected, you go back to the chat from the menu and can chat normally with this application. And I also made the code available on the GitHub for the whole process.
Okay, but for example, when you have your device,
Mhm.
you can connect to Bluetooth or you can connect to Wi-Fi or you can connect to other.
So yes.
How is that different from the normal TCP/IP connection or what?
So it is different when you don't have the Wi-Fi connection is not available. You can still pass the message using the Bluetooth to the nearby devices. And they are in the same chatting room. So basically when you send the message to someone, if it's not in the nearby site, not in the Bluetooth device, nearby Bluetooth devices, you can still send a message. Whenever he becomes again available, he can still see the message. That's the difference between the matrix and matrix match.
Any other questions from the committee? Any questions from our audience? If not, thank you very much. Disinfectant.
Yeah, we disinfect. And yeah, we'll disinfect too. Won't hurt much. Thank you. Who is next?
Jordan?
He never shows up to anything. This guy in a black box. I don't know.
Oh, what?
I was under the door, but I think it's probably
Well, that's like Jay Adamson came in yesterday to do his. He had 0 people show up.
I had 5.
This is going really well this year.
Oh, sir. Good.
Well, it's not like you're applying for a promotion or anything, so.
He's strong to the students, but they didn't want to come. He didn't have any strong opinions.
Yeah.
That's violence anyway.
Well, that's the thing, like, no one even sees it. That's why I try, like, I usually tell students, like, the only person who sees this is me, so if you've got a problem. Like in the comment section, if you got something you really want to say, write it in the comments. Doesn't really do anything.
Yeah, no, you're
I did my GDC talk.
all right.
I was done with tweets about it before that.
Sure.
45 minutes before.
One person showed up at 55 days ago.
Oh.
There's an actual student in English on the
Like,
page.
you don't get your mark unless you.
Another good writing.
That's very good defense, very early in the program. Is there a reason?
The presentations?
Yeah, because
Well, usually we have a day between the end of classes and the beginning
Yeah, I
of
know, but-
exams. That's usually when we do them.
it's less.
Oh, that's-
Because I tell you what
That's-
we've done before, when we
Oh, in CS?
we will do it at the end of the semester. And it's much
Okay.
better because people are more relaxed and people
Oh, well,
enjoy it.
yeah, we always, and I know other departments do it in the kind of between end of classes and their exams. So I was just following what we had done
Yeah,
in that,
but
what we did in
this is
school.
for, well, it's in my case, because I'm teaching even today.
Well, you know what? You bring it up to the next associate meeting.
Okay. Because I didn't know, and you know, short notice,
Plug in.
very stressful.
Right, okay, all right, no, I didn't know
And-
that.
and don't-
I thought everyone had the, between classes and exams position.
Yeah, I should have checked my.
Yeah, but this semester was not. And in the other thing is the students, if they have exams, it's better for them to prepare better.
Whether it was tag wouldn't belong.
Yeah, going forward,
cartoon?
talk to the,
Oh, okay. I've never been a cartoon.
whoever's in charge, not me.
Newspaper.
So what I'd like to do is have a meeting in June, since we're, like, for last session, but I want to deal with that enough. I want to.
Remember, you have to follow the rule for that, which is insert it, doesn't work, you flip it over, doesn't work, you flip it back. It's always great. Yeah.
My lecture is
If I answer that, you do as well.
then I go to
I was just wondering if you wanted to.
There you go.
Are you standing in front of the camera? First night elevator job.
Make sure that it lines up over here appropriately. Yeah, we're still getting a flicker on that. I don't know what happened. Power that on. It's not locked on my side, so what I'm going to do is I'm going to adjust this camera to watch the slideshow. More so than presenter. Yeah, that one is for asking questions. Otherwise, people, their questions you need to stand in front of that camera.
So now when I present, Jordan, should I stand here looking there or there?
No, you should be up in front of the screen
Okay, here.
saying, yeah, giving the intro, because for some reason, now laptops are not syncing properly. Everybody, so every university. Yes, look at the channel.
About ready to back. Every class.
Okay, good morning everyone. My name is Antonio. I'm Jordan's supervisor. I'm going to briefly introduce him. Well, supervising Jordan was really exciting and great. He has been working very hard since the very beginning, even despite the pandemic. And we managed to get some interesting results on, well, controlling exploration on MNAPC. I know it sounds a little bit complex, the topic, and it requires a lot of background understanding. I'm sure Jordan will do that. But the cool thing is that we managed to use machine learning to improve optimization, which is a new field where I'm working. And I just want to mention one thing, one achievement I was able to achieve with Jordan that I was never able to achieve before with an honor student, and is submitting a paper to a top journal on this research. Like just 3 months ago, we submitted a paper that is a result of this honor thesis to an IEEE conference on computational evolutionary computation. So that's a huge journal. We're still waiting for the reviews. It should arrive in 3 weeks, but I'm very hopeful the paper will be accepted. So that's something outstanding, and that's all I will say. I will leave everything else to Jordan.
Thank you. As you mentioned, this is the honors project that we worked on together. We were using a data-centric machine learning approach to control exploration in MNATC, estimation multivariate normal algorithm with threshold convergence. Here you can see the topics that I hope to cover, starting with the motivation, goals, and hypothesis, moving on to some background information, and then experimental information, starting with data prep, moving through classification, and then on to hybridization with its results. Then we'll talk about the gathered conclusions, followed by some thoughts on future work. Motivation. There were a couple of motivations behind this project. We wanted to see if we could replace a portion of a known successful meta-heuristic with a machine learning model in such a way that it could not only improve that algorithm, but also serve as an indication of how similar algorithms might be improved. There was also a raised question regarding the importance of the machine learning model versus the variations within the dataset. Within the context of this problem, we were hoping to see which had the most significant influence. In service to our motivation, we had one overall goal with two sub-goals. We wanted to improve the algorithm, EMNATC, through the use of machine learning, which would replace a hard-coded if-then-else rule, which changes a parameter that guides exploration in the algorithm. That sub-goal would then involve successfully training classifiers to determine the best value for the parameter gamma. Given current and recent information from the algorithm, another sub-goal was to gain enough information to have a defendable problem-specific stance on the data versus model question. Our hypothesis was that given sufficient information and training, in this instance a hybrid using machine learning could perform better than the algorithm using its standard hard-coded heuristic rule. Testing this hypothesis would involve finding the appropriate data with which to train a machine learning model, and determining which machine learning algorithms were the best fit to the problem. A meta-heuristic is a general form of a heuristic. I say general in that it's not specific to a specific problem. They are intended to be usable on a wider variety of problems and so can't rely on a significant amount of problem-specific information. This leads to a trade-off. You can use this relatively widely and easily, but you may not get the best answer. These are especially helpful in computationally expensive problems. They can be used in an effort to guide and/or improve existing heuristics. While they aren't guaranteed to work, they do have a tendency to help and have been found to be suitable in problems involving global optimization. They are often seen as emphasizing two components that were key to this project: exploration and exploitation. They were able to prevent being trapped in local optima so as to find and converge on better solutions. Threshold convergence is the answer to a specific shortcoming of a number of previous algorithms that don't have well-separated exploration and exploitation steps. In globally convex spaces, without that separation, it is too easy to for an algorithm to simply find a local optima and exploit that, failing to properly identify better optima, simply because the sampling and exploration wasn't sufficient and so it converged in one area too quickly. TC uses the idea of a minimum distance, which is applied to between potential solutions and their reference solution. This is used in order to limit the possibility of oversampling a local attraction basin, rather than widely sampling from the available space. When randomly sampling from as many basins as possible rather than favoring one, it is more likely that the eventual exploitation will be within a better optima. This minimum distance is controlled by a decay rate. This is the rate that we are looking to control in this experiment. As the algorithm progresses, the minimum distance will be allowed to shrink. This technique has been used within particle swarm optimization, minimum population search, and differential evolution. We'll see those again in a little while. EMNATC. Before EMNATC came EMNA, which is an estimation of distribution algorithm. It uses distribution function to determine future solutions based on the current generation solutions. Unfortunately, there were times when such an algorithm would prematurely converge. In an attempt to correct this, TC was employed within EMNA's parameter space. If you look at the algorithm, you can see the gamma parameter there. Oh, I'm not wearing my glasses. Sorry. That if-then-else section is what we were looking to replace in this project. Below that is where this comes into play. You can see that the covariance matrix sigma is set by taking the current sigma matrix and multiplying it by the fraction of the function evaluations remaining to the power of gamma. That last part is our threshold value. If the algorithm is still finding better solutions at a single threshold level, that means that that portion of the exploration is not complete and the algorithm is not yet ready to reduce the threshold. If the solutions are not shown to be any better, then it is okay to decrease the threshold. As you increase gamma, you decrease the covariance matrix, which has a relationship to the distance between the new generation's solutions, specifically to their means. So in controlling the covariance matrix sigma, you can control the algorithm's convergence. As mentioned, our goal involved controlling exploration through the use of machine learning. This was set out to be a supervised learning problem which requires labeled data. Since we already know how exploration is influenced within the algorithm, the gamma value changes based on the status of the exploration, it was thought that we could have that gamma set as our label. Example collection came in the form of running through an altered version of the algorithm on the 28 CEC13 functions. In this altered version, the gamma was set to a specific value. Due to time constraints, this was only collected with a gamma of 3. At some random value between 25% and 95% of function allotment exhaustion, that gamma value would be changed. It would be changed into each of the values incremented by 0.5 between 0 and 4, inclusive. Thus, we had 9 different classes. The status before and after the swap was collected for each example. That after portion involved the fitness of each gamma's branch. That fitness was then used in the data preparation stage. When looking at the initial results from the examples collected, there were a number of examples that had multiple potential classes or gammas that would be acceptable as determined by the gamma branch's fitness. Right from the start, we examined how that fell out and determined that there might be issues in including those examples. And the result of this omission was our base. Here, V0 is boxed in and shows the gamma distribution in the remaining base examples. This removal process for V0 removed 1,455 examples, bringing our total examples down to 39,382. Now we can see the V1 variant boxed in now. As you can see, the numbers of each classes reduce as we progress from V1P1 to V1P11. As you can probably imagine, V1 involved further removals of examples. We used a set percentage value represented in the dataset title with the p-value, ranging from 1 to 11. Beyond the removals indicated with V0, each example had their best and worst branches' fitness values stored. If the best and worst fitness values were within p%, that example would be discarded. That caused further reductions shown in the purple box. In V1, we started with 23,930 examples in V1P1 and went to 13,041 with V1P11. Thank you. Unlike V1, V2, boxed in red, did not have further discards beyond those from V0. Instead, V2 used the same percentage system. But anytime an example fell into that range, it would be set to class 5, which was the class used for gamma 2.5, which was the median value. Since there was no further eliminations, each dataset in V2 retained 39,382 examples. Like V1, V3, which we see boxed in black, sees additional eliminations. Like V1 and V2, V3 used the percentage system, but as you can see from the figure, V3 only utilized 3 classes. These 3 classes were for gammas 0.5, 2.0, and 3.5. In order to go from 9 classes to 3, we had to decide which fitness values we would use for each case. We decided that each class would get the average fitness from the 3 neighboring classes, so 0.5 would have the averages from branches 0, 0.5, and 1.0. After that, V3 went through a procedure much like what was found in V1. The best and worst averages would be compared. If they were within p%, that example would be removed. The removal rate was much higher for V3. V3P1 had 17,698 examples, and V3P11 was down to 8,565 examples. Each dataset was used to train 23 classification models. These included 4 logarithmic regression models, one of which is seen on the screen. Nearest neighbors models, one using K, the other using radius, decision tree, quadratic discriminant analysis, 4 neural network models, and others from sklearn's selection. We also had a single run of continuous models, but those only ran on a version of V0. It did not continue past that point as we focused on classification. While each of the 23 model types we went through the entire training and testing phase at classification stage, the 9 listed on the screen are the ones that we used in the hybridization stage. In going through the examples, we went through some feature reduction, ending up with 1,402 features. Using sklearn's train test split method, each dataset was split into 2 parts, a training set of 80% and a testing set of 20%. Each dataset was only split once during the training and testing phase, and so each model for a given dataset, such as V1P1, was trained with a single training set. Using classification testing, each model was trained and then tested using the training set. The model's accuracy, precision, recall score, and confusion matrix were all collected. Of these, the accuracy, precision, and number of classes, as evidenced by the confusion matrices, were given the most weight in determining which models to select to continue. Here you can see one of the logarithmic regression models. The accuracy stayed pretty close to 0.2 until it hit variant 3. There, all models got a boost from switching from 9 classes to 3. And here you can see some statistics from that model for V0. This model type did comparatively well in terms of accuracy, but in terms of precision, it was not very strong. Certainly not as much as other models going forward. You can see here that it only used 3 of the 9 classes for V0. This model was very inconsistent between data sets in terms of how many classes it would use in testing. While the previous model was relatively consistent, QDA was very erratic. It had a comparatively strong showing for V1P11, but very poor showings for V0 and V3. Here's the confusion matrix for QDA for V0. Gamma 0.5 had the lowest number of examples, yet QDA seemed to like picking it. It also selected Gamma 4.0 fairly often, which is fair given that that class had the largest number of examples. Looking at RNN, it was fairly consistent across V0 through V2, and then an increase across V3 with a slight mid-variant decrease. Here we can see the RNN stats for V0. RNN was very consistent. Other than the mentioned chart changes for V3, it kept fairly steady across accuracy and precision. It was one of the models that was always used for all 9 classes, 3 in the case of V3. You've probably noticed that the accuracy numbers weren't exactly very high on any of the examples that I posted here. This unfortunately was true across the board. Other than the random forest model type, all of the models had times where their accuracies were below that of the null accuracy. How many of the model types fell below the null accuracy varied between datasets. It went from a low of 7 model types for V1P7 to a high of 22 for 3 datasets in V3, P1, P3, and P7. In those last 3, random forest was the only model type with an accuracy above the null accuracy. Now we move on to hybridization. We started with only a few models moving on to this phase and then added more as time allowed. As you can see from the algorithm, our modifications came within a certain range of consumed function evaluations. If our progress was between 10% and 70% of the preset number of function evaluations, the model would be sent a vector every 10 iterations in order to update the gamma. Before that, it was hard-coded to 3. After that, it was hard-coded to 4 to help ensure convergence. Each hybrid would go through 30 runs with each of the 28 CEC 13 functions. The fitness and threshold results would be written out to file. In the case of the fitness results within a hybrid, the average over the 30 runs would be calculated for each function. That average would be compared to the average that EMNATC had during its 30 runs. The comparison would show a positive change if the hybrid had a better performance for a particular function, a negative value if EMNATC had a better performance. These differences would be averaged to give the hybrid an overall score. Here you can see a general idea of how the various hybrids did. In this figure, it shows an absolute comparison for each model type, in how many hybrids it had that improved upon EMNATC performance versus how many it had that did not quite measure up. In some cases, the differences between the hybrid and EMNATC was very slight, but this is just an overall picture. This figure is bookended by the two most successful model types in RNN and TF4, which is one of the neural network models. With RNN, all 19 hybrids improved upon EMNATC performance. With TF4, 18 of 19 exceeded the performance. Not one of those 8 successful hybrids from QDA and RF met our internal standard of 10% improvement, which was a goal met by 17 of RNN's models. The other 2 were very close at over 9% improvement. Here we see the table for the TF4 hybrid using V3P9 dataset. This was overall the best scoring hybrid. It had 22.7% better performance than EMNATC. Here it is being compared to EMNATC and the 3 algorithms that we were talking about in the introduction. As you can see from the blue circles, this hybrid had significant success across the board. It improved upon EMNATC in all 3 function types, unimodal, simple multimodal, and composite multimodal, and scored better than the other 3 algorithms in the 2 multimodal sets. Looking at some problem areas, we can see that the other 3 algorithms outperformed this TF4 hybrid in the unimodal functions. It also had some issues with functions 6, 20, 21, and 26. Looking at just a comparison between TF4 and EMNATC, you can see that 4 of the functions where EMNATC outperformed this hybrid, it was by less than 1%. In the other 4, not once was it outperformed by more than 10%. Now looking at RNN had 4 hybrids that had performances that were at least 20% better than EMNATC. RNN had the best overall average among the hybrids, if not the best single score. In this V0 RNN hybrid, we see that the same basic pattern as the TF4 hybrid. The multimodal functions are where it shines. It improves upon EMNATC in the unimodal functions as well. These unimodal functions showed some issues with RNN. It falls behind the other 3 algorithms, and EMNATC had a 77% better performance than this hybrid with function 3. Like TF4, functions 6, 20, 21, and 26 were problem areas for RNN. As mentioned, we also collected threshold data. We can see here that the threshold curves for QDA, TF4, and RNN. Each of the figures included RNN for V0 in blue, TF4 V3P9 in red, which was the best of the hybrids for RNN and TF4. They are joined with EMNATC, the curve for function 4, and whichever curve was in question for the titled threshold curve is in green. You can see that TF4 is almost identical for V3P9 with the EMNATC curve, while RNN converges a bit faster. The better of the QDA curves has a slow start, but then it starts to progress down a bit faster, while QDA for V3P3 remains slow up until the 70% mark, where the algorithm forces it to switch to gamma 4. Even with RNN's worst hybrid, the threshold curve remains mostly unchanged, while TF4's worst hybrid, this one 4.98% worse than EMN-ATC. It stalls early before it picks up. Here you can see 4 figures, V0, V1, V2, and V3. On the x-axis, you can see the various model types. This is showing how the performance within a dataset changes based on the model type. A few quick notes. On the model side of things, RNN always has a better performance than EMN-ATC, a feat not shared by any one dataset, though V0 was close with only 2 models below that threshold. V2P3 had the best dataset average relative difference with 5.69%, and the worst was held by V1P9 at negative 3.6%. We compare that to models where RNN in black had an average relative difference of 15.94%, and QDA in purple had an average relative difference of negative 9.04%. Within this project, we have shown that it is possible to improve upon EMN-ATC by using machine learning. We did this by influencing the algorithm's threshold convergence by having the gamma parameter set by a machine learning model, while it would normally be set by a static if-then-else calculation. Given that this is not the only algorithm that utilizes threshold convergence, the method should be reproducible in other situations. There is evidence to suggest that both model type and dataset changes are relevant to performance within this study. However, the influence of the model does seem to have more sway. While it is important to consider the dataset being used, for this problem, it seems to be more important to select an appropriate model type. We had 109 out of 171 hybrids that showed at the very least some improvement in performance over EMN-ATC. Of those, 32 showed at least 10% improvement. We had 2 notable model types. TF4 was notable because it had the best overall average of at 22.7%. RNN was notable as it showed 4 hybrids over that 20% mark, with the best being 21.67%. Its average percent difference was 15.94%. The next most successful average came from TF4, which had 9.59%. The highest dataset average was 5.69 with V2P3. It wasn't all good news, though. Our intention was to succeed in training good classifiers that could be hybridized to improve EMN-ATC performance. We didn't do this. Our models would not be considered to be good classifiers. 2 of RNN's hybrids that exceeded that 20% mark that were found in V3, V3P3, and V3P11 both failed to exceed the null accuracy. TF4, V3P9, was the highest scoring hybrid, and it failed to meet the null accuracy. Our model type with the highest accuracies was the random forest classifier type, and it had the 3rd worst average performance. So while we succeeded in creating a machine learning hybrid that improved performance, the intended subgoal was not met. We also initially had an aim of focusing on deep neural networks. While we did have some success with TF4 and TF3, those were relatively simple networks. TF4 only had 3 layers, TF3 had 5, but 2 of those were dropout layers. I think that more data would be helpful if one were to look further into deep neural networks. We collected a massive amount of information throughout the course of this project, far more than could be presented here or even within the thesis document. Some of that information indicated that there were areas of the training data that were important, others that needed improvement, and still others that simply weren't required. In order to improve upon this project with the same focus on goals, participants would benefit from collecting more training data. I think that it would be helpful for it to be focused on based on our findings, but also wider. There is evidence to suggest that the initial limitation of gamma 4.0 might have been better had it been higher. There were correlation issues in the data. Some of that might be due to procedures. Some might have other explanations. An exploration into this would also prove to be interesting. We had very limited amount of work with regression models. Working with more of a focus on regression might yield interesting results. It would also be possible to alter the focus of the problem. We were generally focused on classification. This has the potential to be shifted into a reinforcement learning problem, or some combination thereof. Since one of the issues was the resources required to produce training examples, that would be a way around that. And there are the references for this presentation.
Questions from the committee?
Very nice presentation. Thanks very much. I enjoyed reading the dissertation. The results all hinge around this value of 10% that you chose as your threshold.
Right.
That's your null hypothesis that you're working against around testing to see if you've improved or not. Why 10%? And why was that the mark that was put in the ground?
You know, I'm not sure. I know we settled on 10% really early, but
Okay. That's a fair answer.
Sorry.
All right. If you were to change that threshold and lower it, for example, what would the influence be on your results? Overall, to give the shape.
I'm not sure I understand the
draw the
question.
same conclusions.
Well, if I were to start from scratch, I would have to say that there would be a lot of adjustments in the experiment to begin with. But as far as the results, we also had the phase where we just considered all of the models in total, anything that exceeded it at all, and we included that. But most of the models that exceeded it by at least 5% were pretty close to being included in any fashion. So,
So probably not too much.
no, you'd have to go pretty low in order to really change it.
And the last question that I had was about the training data sets that you created.
Right.
You tossed out a number of values over the time that weren't included. What would the consequence have been if you had left those in, do you think?
I think that that would have caused a lot of issues in, I want to say in classification, but obviously there were classification issues anyways. Like, yeah, that was our main concern, is just the confusion that it would have caused, because a lot of the values, it said that any gamma value would have been fine. It gave the same fitness result for all of them. So we were worried about how much confusion that would cause, but again, like our classification rates were really low anyways, so who's to say?
Okay. All right. Thanks very
Sorry
much.
that I didn't have better answers for that.
Those are fine answers. That's great. Thank you very much.
No problem.
Any questions from the general audience?
Lots of questions.
My first question, could you explain the data side? I think you said, but it's not very clear to me. What's the data side? And did you distinguish the training set and the testing set? Did you isolate them? You know, just describe that.
Yeah, we used sklearn's train test split, and right at the beginning, like for each of the data sets, we split it into the 80% and 20%. They went into two separate files, and they were kept separate in that fashion. So each of the models, they were trained with the same training set. So that was all set up. And as far as the training data was went through, there was an algorithm in the presentation. At least I think it was. There. So, an alteration on the EMN-ATC algorithm in question was used to produce the training data. So we went through that. It started, instead of going through the typical process, it had a gamma of 3. And then at some random point between 25% and 95% of function valuations, it branched out. So we had gamma values of 0 through 4 with increments of 0.5. And the values before and after were collected, and that was our training data.
Okay.
So
what's the size? Data size? Size? How big? How many?
How many? It would have been just over 40,000 examples.
40,000.
Yeah.
Okay. The training set will be another 1,000? The testing set.
We used 20% of the 39,000 for V0.
Okay.
That went and was used for testing, and the other 80% was used for training.
Okay, so the total is 39,000.
Yeah,
Just
for
39,000
V0.
was divided by 80% and 20%.
Yeah.
Is that right?
Yeah.
Oh, okay. And you did not touch the testing data during the process?
No, we split it,
Okay.
put it to the side, and that was it.
Okay, I see. Okay, so that's the data set. First question. Second question, I want to ask you. You know, your research is kind of like saying you use a traditional machine learning way, and did not use neural network. You know, the deep learning way. But for the classical one, you're trying to use the data set way, to learning way to replace some classical algorithms such as KNN, right?
Right.
You replace it, you know, to compare. If you use a KNN, and what's the result? And if you don't use something like that, using the data set way, you see which way is better. And your conclusion was your data set way is a little better, right? Is that right?
For this experiment,
Okay.
selecting a model proved to be more important than what we did to the data itself.
Okay.
But that's not going to be necessarily how we go for every single thing. That was just problem specific, really.
Okay, but you tried everywhere, right? You know, all the chosen learning algorithm. You performed that and showed the curve, right?
Yeah.
You showed the curve. Okay. So your conclusion was your data set way, the learning way, is better, is a little better. Is that your conclusion? I want to confirm what's your conclusion. You think you tried this and you think this one is a little better. Is that what you were saying?
I'm not quite sure I'm following the question.
You know, what's your conclusion about this?
Which conclusion?
You know,
We did improve the algorithm itself with what we were using. Yes.
Okay.
And
you adopted. You were saying like a model way,
right.
versus data set way, right?
Our conclusion in that was
Okay,
that the model was more important given our results.
Oh, okay.
So selecting an appropriate model was more important than what we were doing to the data.
Oh, okay. So that's good.
Yeah, we saw the more drastic result shifts based on the model than we did on the data.
Oh, okay. So for using a model is more important, so that you know, your title is like if then else is that kind of like explicit rules, and you want to compare that with implicit rules like a data set. Is that what you are doing this comparison? Your title. What's your title?
Controlling exploration.
Okay, not this one, but there is one saying if then else rule.
Yeah, we had an if then else rule. There, we were replacing an if then else rule with a machine learning model.
Okay. So comparing these two, what is your conclusion?
Well, we did improve on the performance of the algorithm. So we did improve performance using machine learning rather than that hard-coded if-then-else rule.
Okay.
But not included in this presentation, not actually included in the thesis either, I ran separate experiments where I used a single gamma value throughout, and I found similar results. For instance, I used gamma 4, 5, and 6, and with gamma 6, I got over 20% improvement.
You know, I just want to note the last point. Investigate problem-specific importance of model versus data set. So what's your conclusion? Model or versus set? Which one?
For this problem, model.
Oh, model. Okay. No problem for the question.
Okay, thank you.
Any other questions? Thank you very much.
Okay, thank you.
Sorry?
You do that door?
I do not.
You got a lot of other stuff in here over the break?
Well, I've got my lunch with me, so I guess I'll be guarding it except to go to the bathroom. All right, so I just have to sanitize and scrub your face. No, I'm joking.
You're a funny guy, Mr. Vessey.
I try. There are other bits I could have said I would have to sanitize and scrub, but that would be rude. We won't do that here. All right, so that sanitized. I'm going to try something. I'm going to try swapping these two connections. Let's see if that lets it track properly. Okay, bring your unit over. I'll get you wired up. Okay, so that just plugs into your HDMI port. And set your screen to replicate so that you see what it sees.
So, how do I go about it?
That's a very good question. Somebody comes up with first. Okay, looks like it's already doing it, so that's a good thing. Now, just let me quickly check and see what my preview shows. If it's locked. Yes, it's now locked on your screen, which is good. Good, good. Excellent. And okay, so I'm going to put this belt pack on you. First thing you might want to do is lift your hair up, okay? Because this goes around and behind like that. Adjust it, right? So the pads and things. It shouldn't go right underneath. The things should go up here. Those are supposed to be, yeah, they're supposed to be called temporal pins, right? Yeah, like that. Yeah, and then this, you want to go down a little bit so it's close to your mouth. Looks fine. Yeah, as a matter of fact, you can't really see it. You want to attach these yourself, or do you want me to attach it? Okay.
Go anywhere?
You can go anywhere, yeah.
And you answered the question well, is what I'm looking for, but honestly, you know, everything work.
Gordon, can you go to the camera
Now, you said I don't know what
and hit the zoom control and just bring it back a little tiny bit? You can watch it on the inside. No, not there. No. Toggle control above the handbrake. Looks like a slope near the bottom of the microphone.
That shows that you know
Okay, so no, finger towards the back, down, off to your right.
that's what I'm looking for.
Right. Yes, go a little bit W. No, other way. Keep going a little bit more. There, stop. That's good.
It's not necessary, it must be that way.
Okay, is somebody?
Oh, yeah, we're just waiting for Nasser to get back.
All righty. I will mute our microphone.
start. Nancy is here. So Shannon Hill did her honors thesis on the topic dynamics of continuous time mathematical models with Alley effect under my supervision. And this thesis is about continuous time mathematical models, but mostly on qualitative analysis of continuous time models with and without Alley effect. So this is your turn.
Great. Thank you. So as Dr. Islam said, my name is Shannon, and I completed my honors thesis on the dynamics of continuous time mathematical models with Alley effect. So I'll give a bit of an overview of my presentation before I start. So I'll start with my goal and purpose, then I'll move on to some theory behind ordinary differential equations, as well as one parameter family of bifurcations. Many of you are already familiar with that sort of thing, so I'll just go over it briefly. Then we'll move on to exponential and logistic growth, mathematical models, and logistic models with harvesting, what that looks like. Then I'll define the Alley effect, give some examples, and then I'll move on to the really exciting part, the Alley effect mathematical model, as well as the Alley effect mathematical model with harvesting. So the main goal of my honors thesis was to study an Alley effect mathematical model. Now, mathematical models can show us how undercrowding can affect individuals in a population and whether we should allow for harvesting or whether we should lean towards conservation methods. So I begin by considering a first order continuous time mathematical model in the form of a first order ordinary differential equation. So you have dy over dt is equal to f as a function of t comma y, with initial condition y of t naught is equal to y naught. And together we know this as the initial value problem. And when we have the right side of our equation only dependent on y and not dependent on t, we call it an autonomous differential equation. So we have that in 1, and then again our initial condition in 2. So we can solve this differential equation using separation of variables. However, the resulting integration problem is often quite complex, unless it's a simple case. So for that reason, we aim to study the qualitative behavior of solutions of the initial value problem rather than the quantitative behavior. So we're interested in understanding the behavior of solutions without knowing particularly the formula for the solution. So I'll briefly go over what an equilibrium point is. So if we have an autonomous differential equation, dy over dt is equal to f of y, the point y bar, where f of y bar is equal to 0, is called an equilibrium point. Equilibrium points stay where they are for all of time t. Next, sink, source, and node. So an equilibrium point y naught is called a sink, of the autonomous differential equation if and only if the solution of y to t approaches y naught from above as well as below as t goes to infinity. And we call this, sinks stable. An equilibrium point is called a source if and only if any solution from y of t will move away from y naught as t goes to infinity. And we say a source is unstable. Last, we have a node, and a node occurs if it's neither a sink nor a source. Next, the linearization theorem, also known as the Hartman-Grobman theorem. So if we have y naught as an equilibrium point of our differential equation where f is continuous and differentiable, then we have if f prime of y naught is less than 0, y naught is a sink. If we have f prime at y naught is greater than 0, y naught is a source. And then if f prime of y naught is equal to 0, then we have a no test case and we need more information to determine what type of equilibrium point we have there. Now we'll move on to bifurcation. So we'll talk about the one parameter family of bifurcations, which is a family of the form dy over dt is equal to f sub mu of y, or dy over dt is equal to f of y comma mu, where we have mu in the real numbers, and a parameter with y being the dependent variable. So in general, we may hypothesize that a small change in parameter leads to a small change in the nature of our solutions. However, sometimes we see a small change in parameter lead to a drastic change in the long-term behavior of our solutions, and that characterizes a bifurcation. Now we'll go over an example just to really cement the idea of bifurcations, because it will become more important as we go on with the thesis. So let's consider this one parameter family where we have y multiplied by, in brackets, 1 minus y squared plus mu. So if we let mu equals to 0, then we can find equilibrium points where f sub mu naught of y is equal to 0. If we do this calculation out, we get equilibrium points at y equals to 0 and 1. And then calculating the derivative, we have f prime at, or f sub mu prime, f sub mu naught prime of y is equal to, in brackets, y minus 1 multiplied by 3y minus 1. So then if we evaluate the derivative at our equilibrium points, we get what type of equilibrium points we have. So f sub 0 prime at 0 is 1, which is greater than 0, so we know from our linearization theorem that that is a source. And then f sub 1 prime of 1, we get 0, which results in the no test case as a result of the linearization theorem. So now we have 3 cases for small changes at mu equals to 0. So when mu is greater than 0 and small, f sub mu of y does not touch the y-axis at all, and we have no equilibrium points. So we go no equilibrium points, and then when mu is equal to 0, we have 2 equilibrium points, one at y equals to 0 and another at y equals to 1. And then when mu is less than 0 and small still, there are 3 equilibrium points close to y equals 1. One is a sink, and 2 of them are sources. So this tells us that y equals to 0 is a bifurcation point, because we see a small change in mu results in our solution going from no equilibrium points to 2 and then to 3. So just graphically, this will help us visualize what happens for small changes of mu. So each of those solution curves, or each of those curves are have mu for different values. So we have the green curve on top for mu equal to 0.1, so mu greater than 0. We see there's no equilibrium points there. And then red for mu equals to 0, we can see that there's 2. And then blue with mu less than 0, we have 3. So if we look further into this, we see as mu decreases, a second bifurcation point is born at mu star. So when mu is greater than mu star, f sub mu of y crosses the y-axis 3 times, meaning that we have 3 equilibrium points. And then at mu less than mu star, f sub mu of y crosses the y-axis once, so we have 1 equilibrium point. And in order to find this value of mu star where this bifurcation is occurring, we can look to solve f sub mu star of y for 0, which implies that y equals to 1 or y equals to 1 over 3. But since we've already considered y equals 1, we're most focused on y equals to 1 over 3. So now if we evaluate f sub mu star at 1 over 3, we get that mu star is equal to negative 4 over 27. And therefore we have a second bifurcation occurring at mu star equals to negative 4 over 27. So here's a bifurcation diagram, again, just to get a better idea of what's going on. So we see at mu equals to 0, we have 2 equilibrium points at y equals to 0 and y equals to 1. Then moving mu greater than 0, we have no equilibrium points. And then as we move mu less than 0, we see that we have 3 equilibrium points, 2 of which are sources, and the middle one is a sink. And then for our second bifurcation point at mu star is equal to negative 4 over 27, we see that there's 1 equilibrium point right there, and then to the right of that we have 3 equilibrium points. So now we'll have a look at population dynamics as well as the exponential and logistic growth models. So population dynamics studies the changes in populations over time and the factors that influence these changes. Creating mathematical models of population dynamics can help scientists predict and understand the changes within populations of individuals for the present as well as for the future. One of the simplest models that you all already know is the exponential growth model created by Malthus in 1798. So this model is of the form dp over dt is equal to kp, where k is a growth parameter and p is our population size. So we can solve this using separation of variables, and our solution is P of t is equal to P naught multiplied by e to the RT with initial condition P of 0 equal to P naught. So graphically, this is what we're seeing. We're seeing a population start at 0 and tend towards infinity. However, this isn't terribly accurate because we know populations have some sort of upper limit. Populations either tend to run out of food, run out of water, or run out of habitat. So we have something that's limiting our population. So more accurately, we have the logistic growth model that has an upper bound. So this is more realistic for modeling populations. And it was created by Verhulst in 1838. So the logistic population growth model looks something like dp over dt is equal to rp multiplied in brackets by k minus p. So we have a new variable here, k, which is the maximum sustainable population, more commonly known as the carrying capacity. And a general solution for this model is below, P of t. Graphically, this is what it looks like. So in this graph in particular, we have r equal to 0.8, k equals to 25. We see a population starting at 0 and only being able to go to 25, no larger than that. So now we look at the logistic growth model with harvesting. What does that mean? So again, we'll consider the logistic growth model. This time we introduce a new variable h, which is harvesting at a constant rate. And it could be harvesting, or we could be fishing, collecting, something of that nature. So we're curious to know what happens to the population as we increase or decrease h. So we'll fix r, we'll fix k, and we'll vary h. So we denote this function as f sub h of p. To help us better understand the behavior of solutions and how they change when h is varied, let's calculate the equilibrium points for f sub h of p. So we set that equal to 0, we multiply everything out, and we get a second degree polynomial. So we know we can use the quadratic equation, and our solutions are of the form p equals to k over 2 plus or minus the square root of k squared over 4 minus hk over r. So when our discriminant, so the area, what we have under the square root, when that remains positive, we have two equilibrium solutions, namely a sink and a source. Otherwise, if our discriminant is less than 0, the graph of f sub h of p does not cross the p-axis, and we'll find no equilibrium points. So this case occurs when we either have k squared over 4 is less than hk over r, or if h is greater than rk over 4. And solutions where the discriminant is less than 0, we'll see the population become extinct. So from this information, we can determine that a bifurcation occurs as h increases, and more specifically at h equals to rk over 4. So we'll look at two cases. We'll look at when h is greater than rk over 4, the differential equation will have no equilibrium points. And then we'll look at when h is less than rk over 4, and the differential equation will have two equilibrium points, a source and a sink, both close to p equals to k over 2. So in a bifurcation diagram, this is what we're seeing. So we're seeing when h is greater than rk over 4, then we have no equilibrium points. When h is less than rk over 4, we're seeing that we have two equilibrium points. And obviously h equal to rk over 4, we just have one equilibrium point. So in summary, as harvesting increases, we see a decline in the population, and this continues until h reaches the bifurcation value at h equals to rk over 4. So in a fishing scenario, if we allow even slightly more fishing or harvesting, we'll see the population continue to decline slowly, and then eventually it will just collapse and become extinct. And this is quite a frightening scenario from a conservation perspective. We really do need to know about bifurcations in order to understand how much harvesting of a population we should allow in order for the population to remain at a high enough level. So now I'll talk a little bit about the Ali effect, and this is probably a brand new concept to many people. It's more of a biological concept, and it has to do with the the idea of undercrowding in populations. So typically in classical population dynamics, this wasn't viewed as an issue. Overcrowding was more the issue because it was seen that if there's overcrowding, populations run out of food, they run out of water, they run out of space, and that's bad. But undercrowding can in fact also be bad, since with less individuals present in the population, members suffer from less ability to cooperate, and cooperation within a population is important for hunting, for sexual reproduction, and for fighting off predators, for example, and these are all components of fitness. So this results in reduced fitness among individuals, and in this way, individual fitness and overall population size are related. The lower the population size or density, the lower the fitness. And this characterizes an Lee effect. So more formally, an Lee effect is a causal positive relationship between the individuals in a population and their fitness. So in figure part A, in classical dynamics, we usually see a negative density dependence. So as we see the population size decrease, we see individual fitness increase, and that's because typically we think of as a population gets smaller, there's going to be more resources available for everyone. Everyone's going to be healthier and doing better. But in fact, with the Lee effect, what we see is as the population gets lower and lower, individual fitness becomes lower and lower, which can be quite problematic if you think individuals are becoming less and less healthy, we'll say. As the population decreases, we could be looking at a possibility of extinction. So it was W.C. Lee who came up with this idea of the importance of cooperation, and it's him who this effect is named after, although he did not name it after himself. And he's been regarded as one of the central, and this effect has been regarded as one of the central and highly important issues in population and community ecology. And its critical importance has been realized in conservation biology, where the Lee effect is the most likely cause attributed to the increasing extinction risk of low-density populations. And as a result, studies on the Lee effect have received more and more attention from both mathematicians and ecologists, and especially more recently. So within the broad topic of Lee effects, we have two different types. We have component and demographic. Component Lee effects consider the positive relationship between an isolated part of an individual's fitness and population density. So the way I think of it is component deals with one component of fitness. And then demographic Lee effects look at the positive relationship between overall fitness in relation to the population density. And we're really going to focus on demographic Lee effects, because within demographic Lee effects, we have another subcategory of weak and strong. So weak demographic Lee effect may occur if at low density, the per capita population growth rate is lower than it would be at high densities, but it's still positive. And then if we look at the strong Lee effect, we see that populations at low density, their population growth rate becomes so low, it becomes negative, which characterizes a strong Lee effect. So this is a nice visualization of it, what it looks like graphically. So we see the weak Lee effect on the dotted line, and we see that it doesn't cross the x-axis, the population density axis, but then we look at the strong Lee effect, which is the dashed line, and we see that it does cross the population density axis, and the place where it crosses the axis is called the Lee threshold, and when populations end up lower than the Lee threshold, it's generally bad news. So mechanisms are things that cause the Lee effect to occur, and there's lots and lots of different mechanisms, but the main two categories are reproductive mechanisms and survival mechanisms. So some reproductive mechanisms include fertilization efficiency, mate finding, sperm limitation, reproductive facilitation, as well as reproductive investment. And then survival mechanisms include environmental conditioning, which I'll give an example of, predation, as well as aggregation by predators. So it was W.C. Lee himself who made one of the first observations of the Lee effect. And he observed the way that goldfish are able to release chemicals into the environment and the way that it enhances survival rate. And he noticed as there's more and more goldfish in a population, they release more and more of these chemicals that enhances survival rate. But at lower densities, if there's less goldfish, less of this chemical is released and survival rate is decreased some. And now I move on to the LE effect mathematical model. So we have what we had before for the logistic model, except for that last term, x divided by a minus 1. And that's kind of our LE effect term, where we have a new variable a, which is our parameter for the LE effect. So a strong LE effect is characterized by a less than 0, and a weak LE effect occurs when 0 is less than a is less than k. And I should mention too, at a equals to 0, our model is undefined. So to find the equilibrium points for the LE effect model, we can take dx over dt is equal to f of x, solve that for 0, and we get 3 equilibrium points, 1 at 0, 1 at a, and 1 at k. So the first derivative f prime of x of f is right there, and then we can use that to look at stability. So if we evaluate each of our equilibrium points at our derivative, we get that f prime of 0 is less than 0, hence x0 is stable and a sink. Then if we evaluate x1 equals a, we get f prime of a is greater than 0 and therefore unstable, and we have a source at x1 equals to a. And then finally, we evaluate the first derivative at k, and we get that f prime of k is less than 0, so we have that x2 equals to k is stable. So now that we know a bit about the LE effect, we consider the LE effect model with a harvesting term. So we have a negative h as a function of x on the end. There's two main types of harvest we'll look at. There's constant yield harvest, where you're collecting a certain number of individuals that stays constant all the time. And then there's constant effort harvest, which is h times x, where the number of individuals you're harvesting depends on the size of the population. So we'll have a look at constant yield harvest. So we consider dy over dt equal to f of x, where we study a strong LE effect subject to harvesting. So we have f of x equals to basically the LE effect minus h on the end. As we said before, there's 3 equilibrium points here, x0 equal to 0, x1 equal to a, and x2 equal to k. And as before, we can look at the derivative and then look at stability, and we get again that 0 is stable, a is unstable, and k is stable. So it might be kind of interesting to look at how things change when we vary h. So when we have h equals to 0, no harvesting is occurring, and we have the classic strong LE effect graph with 3 equilibrium points at 0, a, and k. If we increase k even further, we get that the unstable equilibrium at a and the stable equilibrium at k move closer together, and we end up with 2 equilibrium points. And then as we further increase h, we see that the equilibrium point at a and k move so close that we only have 1 equilibrium point. And then increasing h even further, we eventually get that we have no equilibrium points, telling us that the population is extinct because we've harvested too much of it. Now we'll have a look at constant effort harvest, and this one's a bit more interesting and a bit more in-depth. So constant effort harvest has the form dx over dt is equal to rx multiplied in brackets by 1 minus x over k multiplied in brackets by x over a minus 1 minus h times x. So now suppose we just find a function f star of x such that we have x star of x, or f star of x is equal to that. And essentially what we did there was just we factored out an x. We can take the derivative of that, so we have df star over dx. Our derivative looks like that. And now if we let our original function f star of x equals to 0, we get a second degree polynomial multiplied by x. So right off the bat, we can already tell that x equals to 0 is an equilibrium point. But to find the other 2 equilibrium points, we'll have to use the quadratic equation, which looks like x on the bottom. So as I said before, our 3 equilibrium points will have x1 equals to 0, and then x2 we have, and then x3 we have as well. x2 and x3 are very similar, just separated by the fact that the last square root term is positive for x2 and negative for x3. So now we define a new variable d, where d modifies x2 and x3. And we have that d is the whole last term, everything, that whole square root term, that's d. So if we plug d into our x2 and x3 equilibrium point equations, then we get that x2 is equal to 1 over 2 multiplied by k plus a plus d over r, and then the same thing for x3, except we have a negative d over r at the end. So now if we evaluate the right-hand side of our df star over dx equation at x equals to 0, we get that big long thing, and then simplifying it, we simply get a negative, in brackets, r plus h. We know that r is always greater than 0 by definition, and for our purposes here, we have that h is always greater than or equal to 0. So we have that a negative, in brackets, r plus h will always be less than 0, so we can conclude that our first equilibrium point, x0, or x1 equal to 0, is stable. Now the other two equilibrium points are a bit more complex because they are in terms of h and a, causing two possible situations to arise. We either have a weak Allee effect or we have a strong Allee effect. And the stability of the equilibrium points will depend on which type we see. So for the purposes of this thesis, we'll focus on the case of having a weak Allee effect. So a weak Allee effect, again, is characterized by a being between 0 and k. So we have three different cases here. We have, so first of all, I'm going to go back a couple slides. So if h is greater than r multiplied by k minus a in brackets squared, divided by 4ka, so that term right there, r multiplied by k minus a squared over 4ka, is what you get if you solve d, solve that for h. So if h is greater than that, meaning that our d squared term from earlier is less than 0, then we have x2 and x3 being complex. So their stability is irrelevant for our purposes. And then if we have h is equal to r multiplied by k minus a squared over 4ka, meaning that d is equal to 0, then our constant effort harvest equation has simply one solution. X2 and x3 are the same, and they are k plus a over 2. And if we go back again to this bottom part, so we have d equals to 0, so that is just simply k plus a over 2. That's where that's coming from. And in this case, using the df star over dx equation and solving at the equilibrium point for 0, we get that we have a unique semi-stable positive equilibrium. Semi-stable meaning that solutions approach from below and move away from above. In our last case, if h is less than r multiplied by k minus a squared over 4ka, meaning that our d is greater than 0, the constant effort harvest equation will have two distinct solutions, x2 and x3, and they're on the bottom there. So let's further consider this third case, because this is the only case we don't really have a conclusion for yet. So since d is greater than 0, we know x2 will always be positive. Then we can simplify the df star over dx equation even further. So we get df star over dx is equal to that first equation. Simplifying it down, we get the bottom. And next, if we plug in x2 into this df star over dx equation, so we plug it in the top and then simplify it, we get 11 right there. And we can notice that df star over dx, evaluated at k plus a over 2, is equal to r multiplied in brackets by k plus a squared over 4ka minus 1 minus h. And that's equal to 0 when we have that h is equal to r multiplied by k minus a squared over 4ka. Therefore, for that reason, we know that there exists at least one set of positive parameters for r, k, a, and h, with a being less than k, since we have a weak Allee effect, such that we can assume that h is equal to r multiplied in brackets by k minus a squared over 4ka minus epsilon, for h less than r multiplied by k minus a squared divided by 4ka, where we have that epsilon is greater than 0, and assuming epsilon is small enough. So then if we substitute this value of h into our equation for d, we obtain that top equation, d equals to all that stuff. Simplifying that down, we get that d is equal to 2 multiplied by the square root of r epsilon Ka. And then from there, if we substitute our h and our d, which we just got, into df star over dx at x2, we get that df star over dx at x2 is equal to that top equation. And then putting our h in, putting our d in, we get that df star over dx at x2 is equal to negative r minus 2 epsilon minus k plus a multiplied by the square root of r epsilon Ka divided by Ka. Since r is always greater than 0, since epsilon we're assuming is small enough but positive, and that last term, that will be positive as well. So a negative of all these positives, we'll get that is always less than 0. And in a similar way, we can show that x3 is positive only when r multiplied by k plus a is greater than d. So that's essentially what we're doing here. We're trying to prove that we do have positive equilibrium solutions because negative equilibrium solutions don't really tell us much in terms of populations. So overall, my thesis aimed to provide an overview of single species mathematical models, focusing on the Allee effect mathematical model with and without harvesting. So in the future, we could look at multiple species models with the Allee effect. Here we looked at exponential and logistic models, single species models, but we could look at multiple species models like predator-prey models with Allee effect, seeing how that would change things if one species was suffering from the Allee effect or if they both were. Or additionally, we could look at competition models. We could look into numerical analysis as well. It might be interesting to understand more about numerical solutions and what that means. And last, we could look at the stability of strong Allee effects with constant effort harvest. Since we just focused on weak Allee effects with constant effort harvest, we could look at strong Allee effects, and that might be interesting. Thank you for listening.
Thank you very much, Anna, for this interesting topic and the thesis you wrote. It was really interesting and enjoyable to read. There are a few things that we need to fix, so I'll give it to Dr. Shafiqov.
Yes.
And he should communicate that with you.
Yeah.
I have few questions, not few questions, but few comments, if you don't mind.
Yeah.
You seem that you used your own terminology, if I say. For example, when you talk about the equilibrium point, my understanding, you meant equilibrium solution.
Yes. Yeah.
So why did you use the equilibrium point? I mean, there is a reason. Why did you insist on using the term?
No reason in particular. No, I should have maybe used equilibrium solutions.
Because it divides the entire plane and you can do all the analysis with that equilibrium solution. The other thing is that, forgive me, I wrote them in my hand. The other thing that you also discussed two main topics in the thesis, which is actually the stable and the unstable case.
Yeah.
But there is a third one, which is the semi-stable. So I'm not quite sure. Is there also another reason that you avoid talking about this?
I'm mostly focused on stable and unstable, just to, because since there's kind of the big two topics that we look at, and there was only one spot where there was something that was semi-unstable, so I felt like it was enough just to give a definition of that, sort of informally.
The last thing I have is that there is an interesting topic on converting a system into a second order differential equation. So if you have a system of first order, you can actually, by differentiating and then you substitute the second one, you transfer the system into a second order differential equation.
Okay.
That sometimes may be solvable or using some technique like series solution, whatever. Did you ever explore that?
No, I didn't look that way at all. I looked more into yeah, more like substituting equilibrium solutions and working from there. Yeah.
Thank you so much.
Thanks.
Any other questions?
Yes, I have. Can you go to like the slides where you're first introducing the harvesting term?
Sure.
So I wasn't like picking up on it fast enough. Is H just kind of like a number here?
Yeah, H is just a constant number.
So what if we are considering like a general function for this harvesting term?
Like some sort of function of x?
Yeah, like a general function of x. So you consider H and then just, I guess the rest of it was mostly focused on H times x?
Yeah.
Right, so what if it's just kind of a general function of x? Is there any sort of like, maybe some papers that you were looking at, or maybe not something that you talked about here, but I guess just any sort of ideas or anything? Or
Yeah, it could be something to look at for future work, but it would be interesting to see if there's some sort of, if we had some sort of law or some sort of rule about you could harvest so many of this individual from a population as a function of x, but no, I didn't look into that at all, but that would be something interesting to look at in the future, rather than just harvesting as a function of x simply. Yeah.
Okay.
Cool.
Thank you.
Thank you.
Any other questions?
We're all from PEI, so we all know that lobsters are very territorial.
Yeah.
So they drive other lobsters out of their territory when they, so I would think the Lee effect would not be very large contribution to their model of population growth.
Probably not, yeah, especially where, yeah, for that reason that they drive other species away.
But we also know that herring and mackerel, you all know this, right, are very social. They travel mainly in schools. So you think the Lee effect would be quite pronounced with those species, which we know recently have just been introduced a moratorium.
Yeah.
DFO has had a pretty shady record of actually modeling species correctly. I'm not sure about cod. Anyone know about cod? Are they school? I don't think they school, but they seem to hang out a lot.
They used to school, but since they decimated the stocks, apparently they don't school in the same way anymore. They've lost that ability.
Anyway, my question is, if schooling was the main cause of the Lee effect in a species, then wouldn't you want some kind of cube root term of the population in the growth model? Because if you increase the population by, say, a factor of 8, you only increase the radius of the school by a factor of cube root of 8, which would be 2.
Right.
So if the size of the school is what is the survival mechanism, I mean, obviously there's some survival mechanism in being a school, or else they wouldn't do it. Probably because it confuses predators, or
yeah.
So would you think it'd be reasonable to look at a special case of the Lee effect for schooling fish and kind of introduce some kind of cube root X term somewhere?
It would be interesting to look at that. It would be interesting just with schooling, because you would think there'd be more cooperation in schooling, and like you said, there must be some sort of benefit to schooling, otherwise why would they travel all together in a group? In terms of a cube root term, I'm not sure about that. I'd have to look into it further.
I didn't notice, when was the Lee effect first introduced?
In the early 1900s, but it really didn't catch on until later, just because it wasn't viewed as important.
I mean, because this was quite a few times, and we always do population with harvesting, but I'd never heard of the Lee effect until your talk.
Yeah.
So it's interesting.
Yeah. Thank you.
Any other questions?
I don't much know your details. I just want to say some comment from an outsider.
Okay.
You know? Okay. So this is a very interesting topic, and I think one thing is, you know, do you think this thing can be related to immigration? You know, Canada's immigration, you know, expectancy. You know, kind of like I heard that there is some kind of plan saying Canada is trying to you know, bring more people in, and so by within 100 years, Canada could be 100 million people, you know, country, a big country, right?
Yeah.
So what you said about this effect could say the population health, fitness, and it's related to the site, right?
Yeah.
So do you think you could like use this to model this, you know, taking some parameters in or something?
Yeah, it's possible. It's possible if we could determine whether having more humans all together actually increases their fitness altogether. Because I feel like what we're seeing more and more now is like the more people we have on the planet, the more issues we're having with feeding everyone and having enough water and enough space for everyone to live. So if you could determine that there's some sort of relationship between the number of people and people being like healthier, we'll say, or having better components of their fitness, then possibly, yeah.
Okay.
Yeah.
I just want to say this is a very great research.
Oh, thank you.
Well, thank you very much.
Thank you.
All right, now we convene for the morning and resume at 1 o'clock with our afternoon session.
Yeah, we still have a couple of minutes.
Welcome to our afternoon session. It's a great pleasure to introduce you to an interesting topic for Queen thesis. Let me give you a very brief review or overview. When you solve, of course, whether you are undergraduate or graduate student or even an instructor, you came across solving a linear differential equation of the second order. The classical way of solving a second order differential equation is a series solution. Now, when you solve it, the differential equation using series solution, the idea is you come down to recurrence relation, and you try to solve the differential equation using this recurrence relation. In general, recurrence relation is not easy to solve, especially if it is higher than three or higher. 3 terms recurrence relation. So in general, it is not really easy to do that. However, most of the classical problems in physics or analytic math or applied math, it comes down to a 2-term recurrence relation. For example, Hermite, Laguerre, Legendre, all this is 2-term recurrence relation. So we can solve it and we come down into what we know are as orthogonal polynomials by terminating the series and so on. So one can ask a simple question. How do I know if I give you a differential equation, how do I know that actually the recurrence relation will have only 2 terms so that I can solve it exact in closed form? And that is what this Queen is going to talk to us about.
Hi, thank you, Professor Nasser Saad, for that introduction. My talk today is going to be on the Chaffet's criteria for second order linear differential equation. The talk will have 3 parts. The first part is just an overview or a review of linear differential equation of second order with 3 parts: the standard equation, Taylor series solution, and Frobenius series solutions. And then I will talk about Chaffet's criteria for 2- and 3-term recurrence relation. The standard form of a second order linear ordinary differential equation takes the form of equation number 1, where px, qx, and gx are continuous functions on some interval s. Now, we say that the linear differential equation is homogeneous if the function g of x is equals to 0 for all x in the set S. In this case, equation 1 becomes that, but the gx on the right-hand side is 0. Now, any equation with gx not equals to 0 would be called non-homogeneous. The complete solution of the inhomogeneous equation 1 is the sum of the complementary solution part, UC of x, and the particular solution, UP of x. And the complementary solution is the superposition of the fundamental set of two non-trivial solutions, U1 of x and U2 of x, of the associated homogeneous equation. The particular solution, UP of x, is any solution of the original inhomogeneous equation. That is to say, that if we want to solve for an inhomogeneous equation, differential equation, we care about the solution of its homogeneous counterpart. Now, the next theorem, let U1 of x be a known solution of the homogeneous equation 2. The complete solution of the inhomogeneous equation can be written in terms of U1 of x, as shown in equation 3, where C1 and C2 are constants. That is to say that if one of two of the solution is known, we can solve for the other one by means of the known solution. Therefore, we will focus on the homogeneous equation. A function f of x with the property that a power series solution expansion f of x is the sum of the power series of x minus x1 to the power of n, and the coefficient c of n is valid in some neighborhood of x equals to x0. It's valid in neighborhood of the point x0 is said to be analytic at x0. In this case, the coefficient Cn are given by that formula, and f of x is called the Taylor series expansion of fx at x equals x0 at point x0 in S, at which p of x and q of x are both analytic, will be called an ordinary point. Any point that is not ordinary is singular. If x0 is an ordinary point of a second order differential equation, then there exists a series u of x, as shown, which satisfies the differential equation within the circle of convergence of the series, has a non-zero radius of convergence, and has x0 and has c0 and c1 are arbitrary constants. The radius of convergence of this power series solution is at least as large as the distance from x0 to the nearest singular point. And for every ordinary point x0, second order linear ordinary differential equation, there are two linearly independent series solutions of the form given by the equation shown above, where C0 and C2, or sorry, that should be C0 and C1 are arbitrary constants. The point x equals x0 in the finite plane is said to be a regular singular point of the second order linear differential equation if and only if the following three conditions are satisfied. X0 is a singular point of the differential equation. P of x has a pole at most 1 degree at x0, and Q of x has a pole at most 2 degrees at x0. And note number 4 is just translating what we have discussed by word into formulas. Now, let lambda 1 and lambda 2 be the roots of the initial equation, where P0 is the limit of z to z naught times z minus z naught times P of z. Depending on the difference of the roots, there can be 1 or 2 series solutions. The 3 cases of the roots is as following. Either case number 1, you have a distinct roots differ by a non-integer. In this case, the Frobenius method produces 2 series solutions. Case number 2, you have repeated roots. In this case, the first solution has the form shown above, and the second solution is it's just dependent on the first solution. So you only have 1 series. For the third case, you have distinct roots differ by an integer. In this case, the first solution has the form as shown above, and the second solution is also dependent on the first solution. However, differ from case number 2, the constant c might be 0. So there can be 1 or 2 series solution. So as shown in the first part, while in solving a second order linear differential equation, one usually encounters solving recurrence relation. It is known that recurrence relations with more than 2 terms are difficult to solve explicitly, and a power series solution for a differential equation are generated by a 2-term recurrence relation. Ensure that that differential equation is solvable. In this part, we aim to establish the condition under which a linear second-order linear differential equation has a 2-term recurrence relation between the successive coefficients of the series solution of a linear ordinary second-order differential equation. Now, let us consider the differential equation above, where the coefficients pj of x, with j are 0, 1, and 2, are analytic functions, and pj of x, it's not equally 0 in the domain of the in the domain S, consisting of all points in an arbitrary neighborhood of x equals x0, except possibly at the point x0. To establish the said criterion, we assume the series solution of equation 2 in a neighborhood of x equals x0, whether ordinary or singular, or regular singular specifically, to be of that form, where lambda is the roots of the initial equation and c naught is 0, and if x naught is an ordinary point, then we can set lambda to 0. Now we will multiply both sides of the equation by some suitable integral power of x minus x naught to the power of m, where m is just an integer, to get equation 12, which can be written as equation 13. Now note that we let p j of x times x minus x naught times m minus j, we let them equals q j of x, with j equals 1, 2, and 1, 0, 1, and 2. Now, the above equation can be rewritten as equation 14, and the problem reduced to just finding the right expression of qj of x that matches the degree of the two sides of equation. So pj of x is equals to qj of x times x minus x naught to the power of j minus m. By expanding q of j by using Taylor's series expansion, we get this. Now we can expand each qj of x as its following series, Taylor series expansion, where the coefficients satisfy the condition that q2 note square times q1 note square, plus q0 square not equals to 0. That is to say that each of the leading coefficients of the three given qj of x, not all of them are equals to 0. Now, the substitution of the aforementioned equation into the original differential equation yields the following expression for the differential equation. The leading coefficient or leading term of the recurrence formula is called the initial equation. The coefficient of x minus x naught to the power of lambda, that is the initial equation, or we can rewrite it as the following if we symbolize our k equals all of this, and that is just the following factorial. Now, similarly, we can take out the coefficient of the term x minus x naught to the power of lambda plus 1, and we can also rewrite it using the symbols that we just mentioned. Similarly, we get that for the power of lambda plus k. Now, we define the function qm of x as the sum from k equals 0 to 2 of the coefficients qkm and the following factorial x k. And note that q note is not 0 because c note is not 0. Now, the differential equation is said to have two-term recurrence formula relative to x equals x naught if the recurrence formula is of the type, as you can see, two terms in the recurrence formula for k equals h and h plus 1, where h is where h is a positive integer, and neither f or g is identically 0 in both lambda and k. Now, given the second order linear differential equation, where once again pj of x or z are analytic in the neighborhood of z nodes, to have a two-term recurrence relation, it must have an expression in the following form. As you can see, for each of the term, we only have two terms left that represents the two term in the recurrence relation, and all the other terms are burned. Now, our two-term recurrence relation reads that now to find a closed form solution of the recurrence relation, we just replace k with hk's, since only the terms that are multiples of h can survive. Thus, our coefficient chk is the product of that. Now, for example, we have the differential equation alpha naught plus alpha 1 of x. So note that the coefficient for the leading u 2 prime of x has greater degree compared to those that are of u prime of x and ux. Now, to extract possible differential equation with series solution that can be computed, two-term recurrence relation, we start by the following. So on the first row, we have the coefficient of u2 prime of x, and that will be, and we will compare or equate that to q2 note plus q2h x to the power of h times x to the power of 2 minus m, according to our theorem. Similarly, we do the same for the coefficients of u prime x and ux. So now we would have, since 3 is the highest degree of the coefficient of u2 prime x, we equate that with the higher coefficient degree, with the coefficient of x of the higher degree on the right hand side, which is h plus 2 minus m. Sorry, number 4 is not supposed to be there. So that would be 3. And our lowest, and the coefficient of the lowest term on the left-hand side, which is alpha 0, which is, and the corresponding coefficient of that on the right-hand side would be q20 times x to the power of 2 minus m, and that would have to be greater than 0 and less than 3. I will do the first case as an example, and the other cases can be solved in similarly. Now, the first case, let's go back to our conditions. H plus 2 minus m is 3, and 3 is greater than 2 minus m, greater than or equal to 0. Now, the first case would be h equals to 3 and m equals to 2. And the first differential equation will then read alpha 3 x to the power of 3 plus alpha naught times u2 prime of x plus beta 2 x to the power of 2 u prime of x plus epsilon 1 of x equals to 0. Now, using the same, now comparing the coefficients that was mentioned in the previous slides, we have q2 of h equals to 3, and that is corresponding to alpha 3. q2 naught is equal to alpha naught. q1h is equal to 3. And that is also the corresponding, the coefficient of x in the term u prime x, and that is beta 2. q10 is 0, q0h is 3, and that is also epsilon 1. And finally, q naught is 0. And thus, the two terms recurrence relation we needed to find using those coefficients is as above. Now, for the Sheffer's criteria for three terms recurrence formula, the criteria is derived in a very similar fashion to that of a two-term recurrence formula. And the theorem reads, for a second order ordinary differential equation, u of z, that takes the standard form or general form as above. For that, the sufficient and necessary condition for such a differential equation to have a three-term recurrence formula, it must be able to be expressed as the following form, and that will conclude my presentation. Thank you.
Thank you for your presentation. I have maybe a few comments and questions. The first question would be, like in your presentation, you have shown us the Sheff's two-term recurrence formula, but for three terms you didn't show any work. Is it because of the time limitation?
Yeah, I decided to take out some slides, and I kind of ran a little fast for some of the slides before.
That makes sense. Yeah. Second question will be from two-term recurrence relation to three-term recurrence relation. Are there any challenges to generalize from two-term to three-term?
So for two-term, you would want to keep two of the terms in this sum that I could show you. So as you can see, m goes from 0 to k, and for two terms, you simply take two terms that are in that sum. And given that q node is not 0, that is the fixed term, and that corresponds to the highest degree term in the coefficient of u2 prime of x.
So the question for me is So to have a two-term, all the terms has to be 0 except only 2. And that's what we try to find a condition under which these two will survive.
Thank you. My final question will be, so you have two-term recurrence relation, also three terms recurrence relation. Is there a possibility that you can generalize it for maybe further?
Yes, the original work by Henry Chaffee is actually for a nth order differential equation. So,
Okay.
yes.
Thank you.
Thank you for listening.
Good afternoon, everyone. So Han is going to be presenting very novel research using, again, machine learning. In this case, we focus completely on deep learning, on improving differential evolution, which is one of the best known meta heuristic for optimizing global optimization problems. But as well, probably you're aware, this kind of algorithm depend a lot on using parameters that need to be set up manually for each optimization problem. And so our approach was to try to use deep learning to automatically set up those parameters. And I must say, the results that Han got there are really promising, and it's definitely something we're going to continue exploring in the future. Go ahead.
Thank you. Thank you. Should I start?
You
can start whenever you want.
So, good afternoon, everybody. So, here's my honors project presentation. And my name is Wang Wei Han. I'm a senior computer science student at UPEI. And in case you want to contact me, here's my email address. So, here we go. So, here's the overview of our thesis paper. Our title is Machine Learning for Parameter Tuning, Application to Differential Evolution. Here, I really just want to show you the table of contents. We have 6 chapters, and the first one is for sure introduction. Then we have some background information about differential evolution algorithm, machine learning algorithm, and then we have the process of creating the data set. We have the training process. We have the optimization experiments part, and then we conclude our thesis paper. And firstly, what is this research about? Firstly, it's in our motivation. So there is a research conducted by Diana indicates that choosing good control parameter for differential evolution will contribute to like good performance. So this parameter selection can be modelized as a classification problem. This is why we think that machine learning algorithm or deep learning algorithm can be a very successful tool in this application. So our hypothesis is provided with enough information, ML model can learn how to address the parameter for differential evolution to improve its performance. We have 3 goals. Firstly, is create a large data set of DE runs for this current research and future researchers on this topic. We design, train, and apply multiple machine learning models for our defined problem. We're trying to test the performance of these models by tuning parameter of D in real time. And this may be confusing if you didn't really get into knowing these terms. So just think about a scenario. Here, imagine sitting in your office, intense craving for coffee just suddenly land in your head. So you pull out the phone, you're trying to find out where is the shortest coffee shop is. The intensity is so bad you want to go immediately. So again, use Google Map to help you find the shortest path to your coffee. So this is very probably just our daily life, right? But to understand what optimization problem is, it is essentially just trying to find out some optimal value in some function. Essentially, every real-life problem can be defined as mathematical function, where optimization problem can be defined as one with the goal of finding the global maximum or global minimum within allowed set. Just look into the graph. We have a very simple function here. The global maximum value is so clear, but in real life, the functions are much more complex than this one. And in many cases, we don't know exactly what this function looks like. Therefore, to try to find out these optimized values, we need to have some solutions. Differential evolution algorithm is a solution to this type of problem. It works by exploring the data set with a population of randomly initialized vectors. They involved by mutation, crossover, and selection, just like what Darwin says, right? So as you can see in this graph, at the first, these populations are randomly located in every part of this function, and they evolve by choosing the better vectors in each iteration. So D has 3 critical parameters: number of population, mutation vector, crossover constant, which all controls the effect of different evolutionary behavior. The value of these parameters have a huge impact on the performance of DE, and they are highly dependent on each particular problem, which is also the motivation of this research. Furthermore, we have machine learning, which is one of the most popular and rapidly growing technical field in our industry. Its success in various real-life applications just motivate our practitioners to apply ML in more under-researched problems, such as the current one. Generally speaking, The machine learning algorithm is just an algorithm trying to take some data and improve by itself to, probably just like that. So to work by the use of data, we need some data set. The data set is a collection of data that used for training machine learning models. Here we formalize the problem of parameter tuning as a classification problem, where decision is made to increase or decrease or keep the same parameter, taking as input data from a previous execution of DE. For our problem, instead of creating a unified problem for all three parameters, we decided to divide them into three subsets and collected data respectively. Therefore, each data set is only responsible for the training data of some models, and these models are only responsible for the tuning of one of three parameters of DE. Here we have CEC 13 benchmark function, and this is so confusing when I first look at it. It's have such complex name for each function, but essentially it's just a black box testing tools in computer science. It's to measure the performance of the target optimization algorithm. In this case, it's where the DE will be run on. It includes 28 different functions in three categories. Function 1 to 5 are unimodal, function 6 to 20 are multimodal, and 21 to 28 are composition functions. So we're trying to use different characteristics of the function to help generalize our models. For the detailed steps of data collection, we firstly randomly set up initial parameter value for DE to perform the first one. And then we slightly increase and decrease the target parameter value for fixed number. For the second and third run, the information of these 3D runs is then stored into a data module, which includes 3 error values. Then it is used for performance comparison. Besides that, we have 13 different features collected at a matrix of 100 times 13 features. For here we have first feature is population replacement ratio. The second feature is number of times the best overall solution has been updated during the optimization interval. And for the 3 to 13, it is the 0%, 10% percentile of the fitness of the current population. For the details of these meanings of each feature, you can refer to the thesis paper. So in summary, we collected more than 200,000 data samples for each dataset. And here is the summary of the data sample by functions for each dataset. The data from function 20 is discarded due to non-error. Here we have, so after we collect the data, we need some way to label the data for the classification purpose. We have 3 categories. 0 indicates stay, 1 for increase, and 2 for decrease. The label is determined by dataset threshold value, which is a critical control variable of our research. We have 2 measurements which is percentage of error value drop. These 2 measurements are defined. So here we got error 0, which is the first D run, the error value of the first D run. And we have error 1 and error 2 respectively as the error value of the decreased and increased parameter values. So this percentage of error value drop is then compared to the threshold value to determine if this improvement is significant enough to mark the label with corresponding behavior. If both M0 and M1 pass the threshold, then the one with the smaller error value will be selected. If none of them pass the threshold, the data will be marked as stay. Because in the first stage of the research, we don't really know these threshold value will have what impact on our research. So we set up 3 different threshold, 10%, 50%, and 20% to compare the effects on the final result. Throughout our research, we are trying to follow the data-centric approach, which is no idea advocated by the Andrew it encouraged practitioners in our field to shift the mindset focus from constantly improve the data, constantly improve the models towards improve the quality of data in a more systematic way. Here we have 3 key concepts: clean up noisy data and error data. We done that by discard the function 20. We have a consistent labeling system, just as described above. We get more than 200,000 data samples for each dataset. And also we set up a stronghold value, trying to play around with the dataset to see what kind of effects will be in the final performance. Here is the summary of data samples by, it's a class prediction distribution for each dataset and stronghold. For each dataset, we have 0, 10%, 50%, 20%. And the interesting thing is, as the stronghold increase, more data are concentrated in state class. So we will describe the detail about this phenomenon in the following slides. Now we move to, now the dataset is created. We focus on the machine learning models. Due to the constraints, we was going to try different machine learning models and to compare the performance. But at last, we only used the DNN, deep neural networks. We designed multiple DNNs with different architectures, with different numbers of hidden layers, with different numbers of hidden units in each layer. And we also apply different improvement terms, such as regularization, PCA, dropout, and batch normalization. However, we dropped these two because of the poor result we received in the early stage of the project. Here, I will do a brief introduction to deep neural networks. And for the deep neural network, we have input layer, hidden layer, output layer. For the input layer, in our cases, the original input shape is number of samples and 13 and 100, but we're trying to apply PCA. So PCA is a dimensionality reduction tools. Therefore, the shape of the data, the shape of the input size will be decreased by the number of components for the PCA we choose. So now this is our new input shape, and the output layer is 3 class, 0, 1, 2. And activation function, we use ReLU, which is the most popular one for nowadays. For the design of our models, we developed a set of architectural options, which is we firstly choosing like different PCA number of components, which will decide the input shapes, and then we create each architecture for each number of hidden layers. So just to let you see, and we have 3 data sets. We have 3 strongholds for each dataset, and we have 40 different DNNs created for each dataset and stronghold. So to improve our model, to see any common technique will result in better performance, we finally used the 2 different the regulation norm penalties. We use L1 combined with L2 regularizer, which is to avoid overfitting by limiting the capacity of the models to regularize its behavior. We also have principal components analysis, which is reduce the dimensionality by geometrically projecting data onto lower dimensions to create new variables. These new variables are called as principal components, or number of components in our scripts or papers. And before the training process, we did data reshaping. We did standardization, which is using Z-score normalization, trying to give the data the overall 0 mean and unit variance. We tried PCA transformation with different number of components. we split our data set into 70% training set, 50% test set, and the 50% validation set. For all the models, we set the values as these, which is used by many researchers in many projects. Then models start to training. Done. It's not that easy. So after we train our models, we have different training metrics. So instead of printing 40 lines, we created aggregated line with a colored range value, which is bounded by maximum and minimum values, where the maximum is highlighted for accuracy and minimum is highlighted for loss. We also created specialized comparison figures for regularization and PCA, where the aggregated line are arranged by their standardized arrow to depict the degree of dispersion of the results. As you can see in different, I'm not sure if it's clear in the here. So these are comparison by regulation and PCA. Here we have our analysis. So the range for most lines are very large, which indicates every models perform differently in different architectures, which confirms the importance of performing such a test to choose the best models. The ranges for regularized models and unregularized model vary greatly in loss and validation loss. And in some cases, as you can see here, the validation loss blows up when we are not applying any regularization, which confirms the regulation is very contributes to the stabilized and regularized model learning. And also for unregularized models, the accuracy will constantly improve, while the validation stays in place or even decreased. So, which indicates the overfitting occurred, and by applying regulation, we can avoid overfitting. For the comparison by PCA number of components, when it's equals to 500, it outperforms the others in all metrics, which is also in accordance with the best models we choose later. So how do you choose the best models? We have these training metrics we have different results. We set up 4 requirements. So the first one is the model should have a good learning curves. A good learning curve represents a steadily rising accuracy and validation accuracy, and also steadily decreasing loss and validation loss. The model also should outperform the other models in terms of higher validation accuracy and test accuracy, and lower validation loss and test loss. The model should have a normal class prediction distribution, where the prediction should not be in extreme cases, such as all prediction are in the same class, which is not what we want. And when 2 or more models have almost the same metrics, the one with less total parameter values, parameter numbers, the less PCA number of components and less hidden layers selected. Because when 2 models have the same capacity, we should always choose the simple one. Here is the best model we selected. We have the PCA N components. Right here, the architectural, and for every data set, test accuracy and validation accuracy keep increasing, and test loss and validation loss keep decreasing as the stronghold value increases, as you can see. However, the class prediction distribution is more concentrated in state class as the stronghold value increases. For now, we have no idea what this stronghold value will be affected our final performance. So we will check later. And the PCA number of components equals to 5 outperform in many cases. Now we move to the optimization experiment. The experiment was organized under 4 different behaviors. We have 3 of which are individual parameter tuning. So this one is only controls 1 parameter at a time. And the other one is apply all 3 models together to tune all 3 models for each iteration. And for the naming clarification, because of we trying to use the existing implementation of DE from Skitland, so we use the same name as they used. So the F, the mutation factor is the MUT, the NP number of population is POP, the CR will be REC in our figures later. We have 28 benchmark functions, but we only trying to focus on 5 representative functions to reduce the time we spend on experiments. The experimental method is, firstly, we have default parameter value set up as this, and we first ran the DE algorithm without applying any ML models for each parameter. So this is treated as control group. As you can see here, as you can see here, this is the result of control group. There is the error value keep fluctuating without any sign of clear improvement. Here, the next we used our trained model for parameter tuning of the all parameters are set as default value for the first, and then the parameters that are not to be tuned stay fixed, while the value of the one to be tuned is determined by the model prediction at each iteration. So when the model predict decrease or increase, a fixed pure change value is used to control the degree of change in the parameter value. Here we set 1 for NP and 0.01 for both F and CR. The experiments with ML are run also running 50 iterations for each version. The above procedure was repeated on 3 different strongholds and repeated on 5 representative functions. Here is the experiment running. So this is control group matrix, and this is the experiment of version mutation. As you can see here, the mutation 0.1 and 0.15 has a steadily decreasing error value sequence. So this indicates these 2 models actually helping the DE to improve its performance. However, for the population parameter tuning, the result is probably the same as control group. We didn't see any clear improvement. In recombination, we can see a good steadily decreasing curve for REC 0.15 model. Okay, so here is our discussion for the mutation version. The mutation 0.1 outperformed all the other 2 models. For the population version, all 3 models failed to see any improvements. For recombination version, the recombination 0.15 outperformed the other 2. And for the together version, the 0.1 outperformed the others. To summarize, among the 4 different versions of parameter tuning experience that use our trained DNNs, 3 of them showed significant improvement in the performance on 1 or more strongholds compared to the control group, from which model mutation 0.1 and the recombination 0.15 seem to be the biggest factor of the good outcome of our results. And back to the stronghold we just talked before. From the final results, a meaningful discovery that although the model with higher accuracy and lower losses does not secure better performance during the deployment. In our specific cases, a higher stronghold significantly increased the accuracy of the model, but such model did not perform well in the final results. To explain this phenomenon, we can understand the stronghold as the boundary line we define for delimiting the dataset with labeling purpose. A higher stronghold indicates more data to be labeled as stay due to fail to pass the stronghold of the percentage of error value drop. Therefore, the models are learned to predict more stay as learned from data. Therefore, these models failed to do more like adjustment in the parameter value. Therefore, didn't perform well in the final results. So to conclude, here is a graph to show you how the stronghold works. Here we have data samples in a two-dimensional data, and we're trying to divide them into different labels. Here's the stronghold for 70%. Here's the stronghold for 50%. So with different line we set up to we can understand the middle part as a stay. So yeah. Here to conclude, the model performs better during deployment when the data labeling system is more reasonable for our defined problems. To conclude, we collected a large amount of data for 3 datasets, such as each of which is related to the effect of change in corresponding parameter values. We set up 3 different strongholds to compare the effect of each on the DNN models and the subsequent D experiments with the trained models. We designed, trained, and tested multiple DNNs for each dataset and stronghold, from which a list of best models was chosen based on a set of evaluation criteria. And these chosen models were then applied to 4 different versions of DE experiments with individual and together parameter tuning, from which significant improvement on the performance were found on multiple versions. For the future work, we can do some research on the reason why none of our models for tuning NP parameter did not lead to any improvement on the performance. We can apply different classic ML techniques such as decision trees, support vector machine, and so on to see if any lead to better improvement than our chosen DNN. We can narrow down the suitable range of the stronghold value and perform more experiments on these values to see which one can lead to the best performance. We can explore the effects of changing the dataset data representation of 13 times 100 data metrics to see if this can lead to any improvements on our problem. That's it. So, does anybody have any question? Thank you.
Okay, so thank you for the nice presentation. So I have a few questions. First one is from your earlier slide where you have data creation steps outlined. So in step 2, you said you slightly adjust those values, increase or decrease. Can you explain slightly?
Yeah. So I will go back to that slide to help explain this concept.
I mean, like, do you just hardcode them, manually adjust them, randomly pick based on functions?
So I think basically we first run the first DE with randomly set up initial parameter value, right? And then we created a ring like with a minus pure change and plus pure change. This pure change is determined is hard-coded by I think it's 0.1 in our cases. For 0.1 for for F and RE and CR. Sorry. And we firstly subtract that value by that per change, and run the second D experiment. And then we again add that value into the parameter value and then perform the third D experiment.
Okay. So my second question would be regarding your selection of 5 functions. So you picked 5 out of 28. So what was rational behind picking only those 5? I can see that you picked 5 to represent all your categories. But why only those ones? Why not others?
These are recommendation from my supervisor,
okay.
Dr. Antonio Luferro. So I didn't really research much into these functions.
Okay.
We were just choosing these 5.
So I assume you randomly picked Antonio?
Well, I picked some of the most famous functions, like
okay.
master genes, sharper function. I tried to pick at least one from each subset.
Okay.
And the problem is that doing these experiments for one function requires a huge amount of computation, so we were not able to run it for the entire for the entire data set. That's definitely something we should do if we want to publish these results. We need to somehow provide results for at least the basic multimodal functions. Otherwise, I don't think this will be accepted anyway. But that's something for the future.
Yes, so my last question is related to PCA. So usually when we do a principal component analysis, we see how much information we want to preserve. So we decide on a threshold and say if we want to preserve 90% or 85 or 80. And based on that, basically, we are looking at the variance that we want to preserve, and based on that threshold, we decide number of components, decide the K components. I see that you have fixed number of components, so say 500 or 700 or whatever you want to use out of 1300. Did you look back what threshold or what percentage of that variance you are preserving with those n components with say 700 out of 1300? What percentage of information was preserved by those number of components, principal components?
No, I didn't look back into. I was trying to do a ground search. Like we firstly set up the PCA components as from 100 to 1020. So I did the first run, and I saw the results are better in the interval between 500 and around 900. So I choose to use them. I didn't really look back into how much variance we preserved.
So, yeah, so that would be my suggestion. You can definitely look back and see if you're preserving whatever 70, 80, 90%, and then you can look into what was noise that was basically responsible for decline in your accuracy, and what is the threshold for keeping those values. Okay, thank you so much.
Very great suggestion.
Thank you.
So Adam Smith is my honors student, and his thesis on the topic of random dynamical systems and their invariant measure using the maximum entropy method. Adam has been working with me since the second year on a number of projects, I had very good experience working with him. He has a publication with me already. Another one has been submitted for publication. Hopefully from this thesis there will be another one. So I'm very happy with him, and the good news is he's going to Waterloo for graduate studies with good funding. So here's your time, Adam.
All right, so like you said, my name is Adam Smith. I'm going to be talking about random dynamical systems and their invariant measures, specifically via the maximum entropy method, but I'll talk about other numerical methods as well. So to kind of preface this whole talk, we're going to be assuming most of the time that we're working within this probability space, where we're in the unit interval, we're dealing with the Borel sigma algebra and usually Lebesgue measure on that. And often we'll be introducing measurable transformations on it from the unit interval into itself. So one of the most important definitions we have to start here is what an invariant measure actually is. So that's the first definition we have here, and it's basically defined so that any set in our sigma algebra, this invariant measure, the measure of the pre-image of any set will be the measure of that set itself. And alternatively, sometimes we'll say that the transformation is measure preserving, because this kind of relationship is between the two things. So it's really just about context. And another important thing that we might define is a dynamical system. In general, I think you might kind of just define a dynamical system as some sort of space with some rule attached to it. But for our purposes, we're being a little bit more specific here. We're working with the probability space that we mentioned, and we'll be dealing with a measure preserving transformation. So I open up right away with an example here, and we're using 10x mod 1. This mod 1 notation you'll see a lot just because it's really convenient for defining these transformations. And essentially what this transformation does intuitively, it's for any number in this unit interval 0 to 1, looking at the decimal expansion of it, it's essentially chopping off this first number in the decimal expansion and shifting it over. So that'll come in handy in soon, but what I'm kind of just showing here is I'm taking an open interval that would be in this unit interval that we're dealing with, and we're looking at the pre-image of it, and we can see that it's this union of open intervals here. And then I'm comparing the Lebesgue measure of each of these things, and we can see that they're equal. So this is kind of one step on the road to implying that Lebesgue measure would be invariant here. But as I note here in this presentation, that's not sufficient because that doesn't apply for every element in our Borel sigma algebra. But in Boyarsky's and Gora's book, there is kind of a result that can extend it to all elements in our sigma algebra. And then this is what the 10x mod 1 map looks like. So another transformation of, or another definition of importance is an ergodic transformation. And I have it defined here. So any set in our sigma algebra such that the preimage of that set equal to that set would imply that the measure of that set is either 0 or 1. So it's either the whole thing or it's of measure 0. And this is kind of important because it gets this idea that we're not going to be, there's no kind of set in this system that's kind of contained to itself under this dynamical system. In general, you might just think about it as not being, being able to be decomposed into these different parts, these ergodic parts. And this example I give here as well, this x plus half mod 1, I just basically proved that this transformation is not an example of an ergodic transformation. But in general, the x plus alpha mod 1 type transformation is ergodic if alpha is irrational, which 1/2 is not in this case. So then we get into kind of the main motivation behind this, and that is Birkhoff's ergodic theorem. I state kind of more general conclusion at the top here, but for our purposes, what this means is that this invariant measure mu of any set in our sigma algebra is actually the relative frequency that points enter this set in the dynamical system. So in some sense, this invariant measure helps describe the statistical behavior of the dynamical system, which can be very helpful in cases where we might have chaos or something, because that can make studying it a little bit more challenging with this unpredictability. So I'm using the characteristic function here, which is sometimes called the indicator function, which basically just takes the value 1 on whatever set you're dealing with and 0 elsewhere. So again, we're going back to this 10x mod 1 example. And so now we get kind of an intuitive notion of what this means for us, is that the length of any set in our sigma algebra is actually equivalent to the relative frequency by which points enter that set under this dynamical system. So again, this kind of just tells us some statistical information about how this dynamical system behaves. And I should mention here, Birkhoff's ergodic theorem holds almost everywhere. So this initial starting value of x that you're using in this transformation is actually kind of important, because you could choose a value of x that doesn't follow this law or this theorem, and if you do that, then this wouldn't actually apply. So you have to be careful about that, especially when it comes to numerical methods. So now we're going to refine kind of our focus to absolutely continuous invariant measures, which are basically just like a specific, more specific class of invariant measure. So we say that a measure nu in this case is absolutely continuous with respect to another measure mu if we have this following. So for any element or any set in our sigma algebra, mu of e equals 0 implies that nu of e equals 0. And in general, you can kind of think about this as one being small implies the other kind of being small. And this is important to us because of the following result at the bottom here. Is if they are absolutely continuous with respect to each other, usually we're going to be using Lebesgue measure as our underlying measure, because that's kind of most physically interesting to us. Then we can define it like this in terms of this function f here, using this integral. And this function f is called the density function of this invariant measure. So, or this absolutely continuous measure. And now we're going to introduce what's called the Frobenius-Perron operator. And the definition there might not seem too important at first glance, but it's really the connection at the bottom that's of importance. So this middle result here that I'm looking at, I'm just considering a specific set, and you can see using that we can kind of rearrange explicitly for the Frobenius-Perron operator using the definition from above. But this result at the bottom is what's important. It basically tells us that any function that is fixed under this Frobenius-Perron operator defines this absolutely continuous invariant measure mu through the means that we just saw using this integral. So essentially what this tells us is we can find this absolutely continuous invariant measure, which describes the statistical behavior of the dynamical system, just by solving for this fixed point of this operator, which in general is a lot more approachable than finding a measure that just has some specific property. So again, we're going back to 10x mod 1 here, and I'm kind of using results we saw for the Frobenius-Perron operator a moment ago, and we get this kind of interesting result. And if we wanted to solve this equal to f of x to find the absolutely continuous invariant measure, we'd still have a little bit of a problem on our hands, because that'd be an interesting equation to solve for. So for the purposes of this, that isn't usually all that useful for us, but we already know that Lebesgue measure is invariant here. So we can define Lebesgue measure like that, because it's a Lebesgue integral. So the function f, the density f equals 1, is what we'd be using. And we can see when we substitute in what we saw for the Frobenius-Perron operator a moment ago, that it is indeed fixed. It's the same when we substitute it back in. And so that kind of just reiterates the fact that this measure here, the Lebesgue measure, is invariant. So now we're going to generalize our understanding of dynamical systems to random dynamical systems. And basically this notation here, the random dynamical system is denoted by T, capital T, but we take whatever transformation, whatever number transformation with probability P of I at each iteration, each step of this dynamical system. And of course, we should have these probabilities that we're taking each of these transformations with. They should sum to 1 as their probabilities. And basically what we mean by IID random maps is that these probabilities are constant. So each iteration of the dynamical system is always going to be distributed the same according to these probabilities. They're not going to change, but we'll kind of generalize that in a moment. And this existence result we see at the bottom here is really just noting that that there is an existence of absolutely continuous invariant measures for these types of maps with some additional condition on it that was proved by Pelican. And here's an example of a IID random map. The only thing that I'm really trying to show off here is how the probabilities work. So we can see that the first probability is a quarter, so that means that each step of the iteration of this dynamical system, we would choose the first transformation with 25% of the time. We choose the second transformation 75% of the time. That's kind of how we iterate through this dynamical system. So now we introduce what are called position-dependent random maps, and these kind of generalize what we just saw, but to functions, where these probabilities are functions of x. So position-dependent meaning where we are in the system kind of affects the probability of what we're choosing for our next transformation. And again, we kind of use this same sort of notation where we take the ith transformation with the ith probability, and of course these probabilities should sum to 1 because they're probabilities. And again, there's another existence result. This one was proved by Gora and Boyarsky. So we have the existence of absolutely continuous invariant measures for certain position-dependent random maps. They have to fit some sort of condition. So our understanding of what it means for a measure to be invariant under this position-dependent random map is a little bit different and not at all as intuitive as it was before. But we can see the definition there. And the definition of the Frobenius-Perron operator of this position-dependent random map is given below that. And you can see that we're actually using the Frobenius-Perron operator of the deterministic transformations inside of this definition. So it's just a combination of these, and the probabilities are inside of the Frobenius-Perron operator here. But what's really important is the connection at the bottom that we pointed out in the deterministic case, that a function being fixed under this operator is what defines this invariant measure. So again, we have this connection. What invariant measures kind of mean to us is the statistical behavior of the dynamical system. So again, solving for this, the fixed point of this operator kind of gives us some statistical information about the system. So here is an example of a position-dependent random map. It's a little bit maybe convoluted. The first transformation there's just a lot of notation going on. But you can see the probabilities that we're using here are piecewise functions. So they are functions of x. They're maybe not so crazy here, but they are still functions of x. And the second probability function, I didn't list it here just because these things take up a lot of space, but you can just take it so that it sums to 1 with the other probability. And the second transformation is 4x mod 1. Again, this mod 1 notation shows up a lot. And this is kind of just an image of what both of these transformations look like. So now I'm going to get into some numerical methods, because in general, finding these invariant measures is very difficult. There's only certain classes of transformations that we can really do this for. So an example that I talk about more in my thesis is piecewise linear Markov transformations. Those are an example of transformations that we can find the exact invariant measure for, but oftentimes it's very, very tricky to do that. So we're often reliant on numerical methods. So our first example of that is the histogram method. This is a very intuitive approach to it. It's basically what we saw for Berghoff's ergodic theorem, but instead of kind of looking at the limit here, we're really just taking a large n. And so what we're doing here is we're defining what are called bins, which are basically just equal subintervals on the unit interval. And we are calculating the measure of each of those bins using Berghoff's ergodic theorem here. And again, what I have to note here at the bottom is that we have to be careful about this initial point x that we choose, because it might not necessarily follow Berghoff's ergodic theorem. In the case of the map that we saw at the beginning, 10x mod 1, computationally speaking, most numbers that we choose on the computer would have like a finite decimal expansion. So if we're going through this process of kind of chopping off the first number in the decimal expansion over and over again, we're going to run into zeros eventually. And then all the weight will be put on zeros, but it shouldn't be. It should be relatively uniform against all of the numbers. So that's why we have to be careful there. This is a histogram of the map that I think I introduced just a moment ago, this one here. So I really just I'm using 1,000,000 iterations in 50 bins here, but we can kind of understand this as meaning like that points in the system kind of go closer to 1 and 0 more often than maybe some set in the middle here, because there's more density put on those sides. And now we have Ulam's method, which is another approach, and this takes kind of an interesting turn. It's not like histogram method. We still are partitioning our unit interval into equal subintervals here. But what we're using here is a finite approximation to the Frobenius-Perron operator in the form of these matrices. So specifically, these matrices n here of K are defined the finite approximation of the Frobenius-Perron operator corresponding to each transformation. So I didn't show any images of what these matrices would actually look like, but it's actually kind of interesting looking at them because you actually get kind of an image of what the transformation looks like. But that's only one step of using Ulam's method for position-dependent random maps. We also have to use this operator Qn here. Each of the components of this vector that you get from this Qn are really just the average of the function along each interval, each subinterval that you're dealing with. And so then we have this important operator at the bottom here called Pn, and this is the finite approximation of the Frobenius-Perron operator for the position-dependent random map. So here what we're doing is we're taking this operator Qn of these probability functions, and we're setting them along a diagonal matrix, and then we're multiplying them with all of the matrices that we found from before. And so we sum those up, and now what we want to do is solve this equation below, where these vectors Fn represent the approximate solution. Here I'm representing them as row vectors, and you can see that it's actually on the left of the matrix Pn here. But most of the time in literature, they'll usually use transposes to kind of make it something you're more familiar with, and using column vectors. But anyways, so this is the result of using Ulam's method with n equals 16 subintervals that we saw for the same position-dependent random map from earlier. Comparing it to the histogram, you can see the same shape, and that's what we should expect, right? So again, this tells us kind of how this dynamical system statistically behaves, where points end up in it. So now I'm going to introduce something called a weakly concave position-dependent random map, and this is just a specific class. This class is nice because we know that absolutely continuous invariant measures exist for these sorts of maps. I'm not going to go through the specific conditions here because there's kind of a lot to unpack there. But essentially, my understanding of this map is really it's just kind of a generalization of an existing type of map in the deterministic case to position-dependent random map kind of case. Another interesting property of this is the invariant measure, or the density defining that invariant measure that you're going to get, is actually going to be an increasing function, which we'll see in a moment here. So this is the example that I'm starting off with. This is a relatively simple one. Again, we're using these piecewise constant probability functions just because they work pretty nicely, especially with Ulam's method. But we can see that this map isn't super crazy or unique or anything. In fact, the only really part that stands out is maybe that first component of the first transformation there, and really all it is a slight bend compared to the other ones. So this can be shown to be a weakly concave position-dependent random map, and because of that, we know that there exists an absolutely continuous invariant measure on it. So this is the result of the histogram for this position-dependent random map. We are using 1,000,000 iterations here in 50 bins like we did before, and we kind of see this increasing pattern like I mentioned just a moment ago. So again, kind of reiterating, this describes the statistical behavior of the dynamical system. In this particular case, we should expect points more often to be around the area 1 than around the area 0. So now we're going to actually introduce the idea of maximum entropy. Maximum entropy methods on their own are applied pretty much all over the place because it's very versatile, And specific application depends on whatever context you're dealing with. In our case, we'll kind of develop it in a moment here, but it basically kind of just runs off this idea, this maximum entropy principle. So kind of loosely speaking, the set of all sort of distributions or densities that you could look at that kind of follow from this, whatever data that you're given, the one with largest entropy should be the one that best represents the data, because in some sense it makes the least assumptions about it. So we're using a Boltzmann entropy functional. There are different definitions of entropy, but I think most of them that you'll see kind of follow a very similar format, this negative sum of f ln f. In our case, we're using it over the unit interval. So this is what we're going to be using in our method. And to actually begin formulating this maximum entropy method, we first define what are called the B-splines. And to start defining those, we first define a bunch of nodes along the real line that are equally spaced. And then we can use this recursive formula to define these B-splines. And I make a note here at the bottom that in general, you don't need to use this formula for every single B-spline that you're going to need in this method. You really only need to do it to generate a specific B-spline of a certain degree. And then you can find all the other ones just by using translations. So this is kind of an image of what these B-splines look like. The first one is really just showing off what different degree B-splines look like. And the second one is more in line with what you'd use in the actual method. Specifically, we're using linear B-splines here. We can use different degree B-splines if you like. But you can see that these are all kind of translated from another. And another thing to point out is that it's being contained to this 0 to 1 unit interval. Some of these functions, like per se this green one, would naturally go continue on outside of this unit interval, but we don't care about that stuff. So we kind of just restrain it to that. And now we come to the formulation of our actual maximum entropy problem. And so to do that, we first look at density functions, which we are kind of just thinking as non-negative functions with integral 1. And this is kind of the normal way that you might define moments in other contexts. But the moments of some density function f with respect to these B-splines is given like this, specifically again over the unit interval. And we're going from negative k to n minus 1, which might seem a little bit strange, but that's just the indexes that you'd use to make the B-splines actually cover the unit interval properly. So then our constrained maximum entropy problem is given like this. So now what we are wanting to do is maximize the entropy functional we saw before, such that f is the density, which is what we want, and that these moment conditions should be fulfilled. Now, upon first glance, this might seem a little bit counterintuitive or a little bit circular, perhaps, because we need these moments in order to find the density function, but we need the density function to find the moments. So a little bit confusing, but we have a workaround for that in a moment here. And we have an approximate solution given by this, because in general, these maximum entropy methods for these constrained moment type problems are pretty well established, and the solution follows this form for our case. And we'll see that we have these constants Ci, and kind of a big portion of our method is actually solving for these, because once we do, we have the solution to our approximate solution here. So our algorithm is outlined like this. We start by choosing n, and we partition our unit interval into n sets, and then we choose k and generate these B-splines accordingly. So what we kind of have control over in this method is how we choose n and how we choose k. And then we're approximating the moments like this, and this is basically an application of Birkhoff's ergodic theorem, again using a large n, and again we have to be careful about this initial starting point x here. And so really what we're doing here is we are considering the trajectory of this position-dependent random map, and then kind of counting how many times, well, I guess we're not counting in this case because we're not using characteristic function, but we're using B-splines of each of those iterations and summing them up. And then once we have all these moments, we can kind of use the definition of the moments that we saw earlier with the approximate solution that we also saw just a moment ago. And then we have this system of equations that we can solve for these unknown constants. And in general, this is kind of where the cost of this method comes from, because we're having to solve this nonlinear system of equations, and that can be it can take quite a while. So you can do that using any sort of type of system solver you want, like Newton's method is sufficient here. And then once you have those constants CI, you can just form the density. So the convergence of this, not something I'm really going to talk about too much, because it was proved by Borwein and Lewis in general for this type of entropy functional. But for our specific purposes, we have this convergence result at the bottom here. And to kind of explain that, we use the L1 norm, which is really just a Lebesgue integral of the absolute value of this function over whatever set you're working in, and for us that's the unit interval. So we have this convergence result at the bottom here, basically saying as we increase n, this should converge to the exact density function that we should have for this system. So this approximate solution essentially is an approximate solution or approximation to the invariant measure that describes statistical behavior of the system. These are results of the method here. This is using the weakly concave map that we saw just a while ago. I'm also showing Ulam's method here, but you can kind of just see all the methods compared. Kind of one difference here is that the maximum entropy method is continuous. The other one's piecewise constant. Maximum entropy method we're using here is for k equals 3 and n equals 4. Again, we can kind of play around with these parameters as we wish. And here's another example of a weakly concave position-dependent random map. This is a particular instance of a map where we can find the exact invariant measure for. So again, I'm taking the second probability just to sum to 1 with the other one. And these are what the transformations look like. One of the important properties of the weakly concave position-dependent random map that I didn't really talk about is that the intervals here, we're dividing this into kind of 4 equal subintervals here. The transformation should be 1 at each of those endpoints, the right endpoints. So that's kind of specific sort of information about this type of map. And since we know the exact invariant measure here, we can actually look at the table of errors, and we're kind of calculating those using this L1 norm that we saw before. And we can see for a fixed value of k, as we increase n, our errors are getting smaller, and this is exactly what we should expect from this numerical method. There's kind of a little bit of a difference between the different values of k. In this case, it actually looks like k equals 3 is worse than some of these, which is just kind of a little bit strange. But if we were to do further studies about this, it would be of good interest to kind of study how exactly k affects our solution specifically. And another thing that I'm talking about in this conclusion here is that this, of course, avoided any talk about the rate of convergence. That is something that would be pretty important for us to establish if we really wanted a proper comparison with other methods and in general the method as a whole. But to kind of summarize everything that we've kind of just listed here, what we're doing here is approximating the solution of the fixed point of this Frobenius-Perron operator, which defines the statistical behavior of this dynamical system. So that's everything, I believe. So we have some references here. Thank you for listening, and if you have any questions, then you can come up here and ask them.
Two pages of the questions.
Oh, man.
Not really, not really. I'm only going to pick a smattering of these questions to ask you. So, I would say it was a very well written piece of document and very well presented survey of the area of random variant measures for dynamical systems.
Mouthful, yeah.
Wasn't clear to me. Statistical mentioned that you have some independent or original results, not just survey. Wasn't clear to me when I read the pieces if any of that was original work, or is that, I mean, there's no requirement for that.
Just like the original result of position-dependent random maps, or none of that is original. No, this is all established in other papers. So.
What about the examples?
Examples, I'm pretty sure all the examples are mine, because you can kind of make them up on your own. But the important thing about coming up with examples is figuring out whether they actually satisfy conditions to have absolutely continuous variant measures.
So I had a question about that. How rigid are your choices for examples? For example, with the Ulam's method, when you approximate it by block matrices where each one is a multiple of an identity, that's because you're piecewise linear, and you map endpoints of partitions to endpoints of partitions. If you just wiggled those a bit, you would no longer get multiples of identity, but you would get diagonal operators close to identity. Could you analytically analyze those ones?
I have no idea. I would have to look into that more, I guess. But, right off the top, I don't think I could really answer that.
Okay. Things just occur to me. So
yeah.
Can you go to the slide where you define the Frobenius-Perron operator? For back at the start.
Okay.
There it is. You can interpret that equation at the top as an inner product equation.
Oh.
P tau f, inner product characteristic function of E, is f inner product characteristic function of tau inverse of E.
Okay.
And tau inverse of E is related to what's called the composition operator. It's
is this the Koopman operator that you're talking about? The Koopman operator? Is that what you're talking about? Because there is this notion of the Koopman operator is the dual. Yeah.
This is the adjoint.
Yeah.
So Frobenius-Perron is just the adjoint of that operator if you think of it in the Hilbert space.
Yep.
There's a number of conditions, and I'm rambling a bit here, on the spectrum of composition operators. There's a number of results.
Oh, okay.
Your speed of convergence, in my sense, maybe Chapel can clarify, once you take out the eigenvalue 1, the rest of them are inside the unit circle somewhere. The smaller they are, the faster you will converge. So if you knew more about the spectrum of the Frobenius-Perron operator, and maybe going over to this composition operator would help. I mean, you know it's a contraction from L1 to L1. Do we even know if it's bounded from L2 to L2?
Actually, I don't know. In general, I don't know.
So, I mean, all this would have to be done in L2 because its correspondence is all in L2. L2 is inside L1, so it's definitely defined there, but whether it's...
Yeah, most of the existence results are really just defining some sort of bound on whatever norm you're dealing with, so...
Anyway, so that was just something that occurred to me. The other thing, you mentioned it, maybe, I can't remember, maybe I made a comment in my, I already said Adam some small changes to the thesis. I might have mentioned the row vector versus column vector thing there. If you just interchange your I and J, when you define the entries, everything goes to columns. This is not a standard thing. Markov chains almost always use row vectors, but then in every other part of linear algebra we use column vectors. So I mean, it's kind of a weird thing. But let me just find one last question here. Leaf B-splines. They're a partition of unity. What other property do you need to make B-splines work in your maximum entropy?
I would imagine that it's this basis property that they form the basis of the piecewise polynomials on that space. That's what I would assume.
So basically, you know, if that was just a choice, that there's probably other choices.
Yeah, you could use other choices. Like you could use monomials if you want, but they don't follow that partition of unity property. So they don't work very nicely. But they might in different methods depending on how you work with things.
Okay, thank you. next speaker is Isaias Casa, who was supervised jointly by myself and Chris Power. He's going to talk about the development of a puzzle game.
Perfect. Okay, thank you. Yeah, so in this presentation, actually let me just quickly talk about the table of content. So I'm going to talk about the introduction to what basically I did in the honors project, and then the development sequence steps that I had to take, and then hopefully I can give you guys a demo, and then some of the future work that we plan to do with the app, and then finish it off with a conclusion. Yeah, so for introduction, basically for my honors project, I developed a 2D puzzle game using the Unity engine. It was basically inspired from Professor Gordon, and it basically involved a theory of fast matrix multiplication algorithm. So basically, let me quickly explain what the fast matrix multiplication is. So basically, the normal one is matrix multiplication, which is, in a sense, we're multiplying two matrices together. However, when I don't know how to pronounce his name. When Sternson came along, he found a way to multiply two by two matrices in 7 steps instead of 8. So, so this kind of logic, that the way that we're adding and subtracting here, as you can see in the grid, is what actually inspired the game to be created. So yeah, so from this information, you guys kind of have an idea that we're gonna take some type of math or some type of grid to change it to a game. So basically, that's what I'm gonna be talking about, the steps and the journey that I took. So for the development sequence, basically my first stage was requirement analysis, where I talked to the client and my supervisor to make sure I'm solving the right problems, which actually did not happen the first time around. Professor Gordon gave me a description of the game. I went back and I solved a completely different game and came back and they told me that's not even the game. So it's very critical to take your time in that requirements analysis stage, just to make sure you have the right requirements and you're solving the right game. And then I moved on to system design, where I kind of designed the interface, the backend, the logic, and then went to implementation and then testing and development and maintenance. And also another point I'll point is, if I got a chance to redo this honors project, I would have gone with a more agile approach, where I would have broken down the system into sprints and basically finished them off with sprints. But this is the process I followed for this time. Yeah, so for requirements and analysis, basically I broke it down into two functionalities. One being just the normal functionality. For example, if let's say we take the navigation requirements, basically that navigation requirements needs to allow users to access the main page. So all the requirements I listed out for each section, what the game needs to do, and basically that'll be an example of a functional requirement. So for each function of the game, what it needs to do, I broke it down into requirements, and each function has its own table. But this is just an example of the navigation. And for the non-functional requirements, so this is basically the general requirements that the game has to be a fun gameplay, which is actually very emphasized by the client, and we'll see how we're going to add on the future work to make the game more fun. We also have to produce a prototype that can be play tested. So in the case that they want to test the game. And also we have to keep the speed, the platform, and also another key part is the documentation, which I kind of don't. I'm not the best at keeping documentation myself, so I'll admit to that. Yeah. So for the user interface design, basically it involved thinking about the navigation, the layout, the structure, the icons, the aesthetics, and then by the end of it, you should have some type of prototype, which I'll show in the next slide. So this will be using the screen path modeling, just to kind of model the structure of how the navigation works. So basically in this sense, I use the pyramid model just because I don't have that many screens. So basically I just need a home screen, be able to choose difficulty. From that difficulty, go to the game scene and then go back to settings. And basically I just need one level below the root level. So basically that's why I chose the pyramid structure. Yeah, and also I went on using Figma. It's basically a user face design tool to design just this simple interface before actually going into the implementation stage. And basically this kind of looks like the game, but it doesn't have the functionalities behind it. And next I had to choose. So once I had the design, I had to choose the engine or the game engine to be able to code that, to implement that design. So basically I used Unity. The reasons because of that is because Unity has Unity assets. So assets you can use like the icons, like buttons, already made buttons that you can just plug and play with. And also a lot of reference that you can kind of see how people do things and how they use Unity optimally. And also it's very beginner friendly, especially people that do game design. They know that Unity is a little bit more friendly than, like, let's say OpenGL or other game engines out there. And also it has a big community. A lot of games are developed using Unity. Yeah, so implementation stage. So here the things I was thinking about was good programming practices, thinking of how can I use design patterns to better optimize the game, and also I was trying to think of how do I model it, like how do I get a model. So basically I went with class structure just to kind of see how those different classes will interact with each other. So basically this is just a managerial class diagram. There's a whole lot of different stuff, but just to show you here, for example, good programming practice or even a design pattern I used here is like I have like an is savable interface, which is basically any class that needs to save data needs to implement that is savable interface, forcing it to have that save method, right here. So that in the case where I have like a save manager down here, so basically this uses a subscription method. So whenever the game manager is created, or let's say the sound manager, they subscribe to the save manager, and all the game needs to do is, let's say when it closes or whatever, all the game needs to do is go into the save manager, iterate through all the subscription that I have, and just call the .save method, which I forced them to implement in the first place. So that's like one of a good example of using design patterns and using good programming practices. And also I did model it with an activity diagram. So in this case, like this is just the basic model. So for example, the start to be right here. So when the game started, all these things get initialized, and then at some point, let's say the user chooses a game, they go into the lobby, and then they can, let's say they can choose a game, they can continue a previous game, and so on, and which I will demonstrate in the demo. Yeah, so after all that, after designing the prototype, after designing the class structure, after putting everything together, we end up having something like this on Unity. So basically this is the game screen that users are going to be interacting with. As you can see here, this is the level easy. Here we have the number of moves currently the user has made, and then we have like a little timer here. And this is basically the grid that we're trying to solve. And these are the options that we can use to be able to solve this grid. And solving this grid means turning all the numbers to 0, which I will demonstrate on what to do. And we do have functionalities like calculate and undo if we ever need it. So yeah, so I'm sure the question that's coming up in your head is, how do you generate the puzzle? So it's actually pretty easy. So what we end up doing is we do these kind of random but not random moves. So for example, let's say we just choose, okay, pattern 1. Pattern 1 would be like this pattern and a positive. So these options actually have the option to be positive or negative. So we can inverse their sign by just double clicking on them. So if we choose the first pattern, the positive, and place it in the 0, 0, the upper left of that box being in the 0, 0, and then the lower right being in the 3, 3 position, and so let's consider this being a move, okay? And then we do several moves like that, and then by the end of it, what ends up happening is we have this generated grid at the top, and basically, if we invert that grid, basically just negate everything, we have negative of basically this grid. And now, if we went back and did all the moves that we did to get to this position, it solves this grid. So basically, if we went back and did all the steps to this grid will turn to 0. And to make sure that the user is able to, like, let's say they make one move, because there's so many moves, if you make a different move than the move that we don't have up there, it's gonna take you to a whole different route. So to be able to make sure that the user can still solve it in, let's say, a lot more moves, we add this functionality of a star, which basically means it's a free cube. Basically, nothing gets affected. So you can drag any options grid on it, and it will still stay a star, meaning it's basically a 0 even if you add or you subtract on it. And these things are better explained when I play through the game. So yeah, so let's play the game. Yeah, so basically this is the hopefully you guys can see it. Yeah, so this is basically the game. So when the user first comes in, they're produced with this initial screen, and this continue button is just, I played this game previously and I didn't finish it. So if I go to continue, I continue where I left off with the time, and I made 4 moves and whatnot. But let's say for this demo, we start a new game. We choose easy, and then we're introduced with this puzzle info, telling us what the puzzle is that we're about to solve. So basically, the puzzle level is easy. The grid shape is a 4x4 grid, and normally it might not be optimal. Someone might have a chance to solve it in less moves, but you can definitely solve it in 5 moves. And the best time it has been solved is in 60 seconds. So basically, I'm gonna try something. So I'm gonna try to do the first couple of moves, and then I'm gonna get someone from the audience to help me finish up the move. So finish up the game in a sense. So basically here, what if I was a user, what I'll do is I'll try to analyze how can I use these options down here to reduce this grid to 0. So firstly, I can look at I can make a move like this. So for example, if I choose to drag this over here, and I choose to drag this on top of, like, somewhere here, I see that so this is a free square, so nothing happens here. Even if we add, it's still going to stay a free square. But I see that here I can get rid of 1. So basically this will become -1, and this will become -1. However, I do add another 1. So I'm kind of going in the right direction, so I'm just going to go with this move. So I press calculate, and I have the move, and it goes back down. So now I see that I can perhaps use so a 1-1 here, so a 1-1 here. So I can perhaps use this grid right here to get rid of the corner moves. So basically this will get rid of this move right here. So I get a 0, 0, 0 here, and basically this is how we're trying to solve the grid. So from the audience, if you can see another move that we can make right now to better position ourselves to be able to win. Any moves? And remember, we can change the parity of these things too. So like for example, in this case, I can try to get rid of these. So for example, I can do something like this. Oh, sorry. Wait. So I can do something like this. Get rid of the 2 and the 1 here. So that kind of leaves me with this. So what do you think I should do next? What pattern should I put here or here to get rid of these numbers that we have? So try to get this 2 down to a 1. So basically, yeah, so we can kind of use this, right? So we can kind of pull this guy right here and basically just change the parity. So that kind of gets rid of all these and gets rid of the 1. So that kind of helps us. So basically now we're left with these 2 guys right here. And remember, this is a free square, so nothing happens here, even if we have something there. So basically at this point, it's kind of might be obvious. So basically this guy, we can drag this guy up here, put him down here, change the parity, and voila. And we do have sound, but I'm not sure why it's not playing. But yeah, so basically now we're able to solve it in 3 minutes. It tells us the new difficulty and whatnot. We can decide to go to the home page. We can decide to create a new game and whatnot. And we can also see our high score here. So we played 23 times. Our average time is 3 minutes and 18 seconds. And the best time is 06. We can also change the volume. Yeah, so we can turn off the sound, turn on the volume. The music is just like when you kind of win, it's like that music it makes. So we can decide to turn those off or on. So basically that's the demo. Yeah, so future work. So basically the game doesn't currently have a global high score. Well, so we do plan to make this game like post it on the App Store. So we kind of have to create a global high score system where people can interact and see, oh, who's solved this puzzle, who solved what. But also, we also need to work a little bit on the responsiveness side. As you can see, it's a little bit buggy when you play it. So just polish the app a little bit more. And also maybe provide a system of buying points. So for example, if you're stuck on a puzzle, you can use those points to unlock a puzzle or things like that. So that's a whole new logic. And also I mentioned we're going to make it public. So maybe we can use ads here to revenue to make revenue from the game. And this is the biggest one. So basically, my client, Professor Gordon, wants to make this game more fun. So basically, try to get rid of some of the numbers there to make it more fun. So basically, the same logic will apply, but in a sense of it's like Tetris. So basically, it's going to be different cubes that you can stack on top. You can decide to stack them or reduce them, like we did with the numbers. And basically, it's going to be a Tetris game with 3D cubes, basically, and the goal is to not have any cube on the grid. So that might be a good way to make the game more fun. And also, we want to think about user accessibility. Try to get as much different type of people to be able to play the game. That's something that we're thinking about. And also work on the development of the hard level, which is kind of different because the hard level has like two. So basically, that easy level of the two grids, you're solving two grids at the same time. Yeah, so just work on that level a little bit more, and yeah, that's pretty much my my honors project from point A. So I was so basically, hopefully, I made a good presentation on driving you through from A to B, basically from that idea stage of Professor Gordon to at least a prototype stage that we can kind of play, and it's just for the honors project. It's not just having a game that inspired me; it's also inspiring other people to create their own games and see how easy it is to create games on Unity. Yeah, so that's basically it, and thank you for listening.
Gordon had a couple of pages. I'll bring a whole question. So I'm kind of I'm glad that you made a comment today in the presentation, but in the thesis as well, you said if I had it all to do over again, I wouldn't have followed the waterfall method. I would have followed an agile development method. But then what's the reasoning why you would have followed the agile method?
So the reason why.
Agile method, I should say.
Yeah, that's a good question. So the reason why I said agile was because of we're able to pick up on those wrong mistakes quickly. So because with the more of the traditional model, what ends up happening is the client gives me a description of what he wants, and then I'm doing all this work thinking, oh, that's what I'm solving, but I'm never going back to the client to make sure those things are being done. So the great thing about agile is you kind of break it down into sprints. So for example, let's say I talk to the client and says, okay, I want the homepage done. And I go and then get the homepage done. I go back and show him, he doesn't like it. We can throw that away because we only spent like a few weeks designing that instead of waiting a whole.
I think there are agile methods that don't necessarily use sprints or time-based tracking, but I think a lot of them do try to pull that client in closer. So when you showed the Figma results, were there a bunch of iterations that the client would have said, I like this, but I don't like that? Or was it sort of like, we did this modeling, and then at the end the client said, yeah, all right, if you've done a bunch of work, we're going to use that.
So yeah, so that's where I made a mistake. So I was not too active with the clients to make sure of those preferences for the client. So that's why I said if I had to redo it, I'll basically break it down to that just to make sure specify those client requirements.
One thing that's interesting, because so I've known about this project for a little while. So Gordon's been working, I think you mentioned to me before. In my mind, Gordon's interests, I didn't speak to him about his interests, but in my mind, Gordon's interests were to beat Strassen's fast multiplication, discover something such that you can get a better matrix multiplication algorithm. And so I was kind of reading the thesis and waiting the presentation that have we thought about storing data, or how is that going to allow, where does that figure into the long-term plans, and or has it figured in yet? And I do see like there's maybe some plans for buying hints or displaying ads or like, a lot of gameplay stuff, but is there a goal for the data on the backside of that?
That's right. So basically, it kind of looks like, at least for the easy level, that computer can be able to generate those patterns, right? However, when it comes to solving two of those grids at the same time, it kind of becomes difficult to solve those in algorithmic way. So basically, the next stage is now trying to research how we can use algorithms to generate those good patterns. For example, in the next level that I didn't show, there's two grids instead of solving just one grid. And basically, at least to my knowledge, there's no known algorithm that solves those two grids at the same time. So basically, that's where the research I think will go.
Sure. It's a challenge because I do have a lot of questions about the game. Like, is there heuristics that you know, because as a person, and when you played the game, we could see some heuristics like, oh, these big numbers are going to try to maybe lower them down, or I'll use some operation that gives me the most bang for the buck, or gives me, you know, some sort of greedy approach or something. So there could be some heuristics that maybe don't get you quite there, and then in your thesis you say maybe a little human intuition. But I guess my last question I'll just say is, given that Gordon's kind of had this idea in his back pocket for a while, but then this is maybe the first time that that we've used software engineering to try to get there. Did we get further to the, did this get further to what your envision was by using more systemic development approach?
Well, we had to kind of go away from, we decided on a smartphone approach pretty quickly. And the grids for the actual solution of the fast matrix multiplication problem were just too big to put on smartphones. There may be some data that can be mined there for some intrinsic ideas about generally solving, but we can't go up to that big size and make the game.
I see. So gameplay became more focused because of the screen was small. Okay, yes, that makes more sense. All right, anyways, no, thank you very much. That's all I have. So.
All right, thank you.